Hey, so here is the thing nobody tells you about planet Earth. It is showing off. Right now, somewhere on this planet, a volcano is building a brand new island from scratch. A waterfall is carving a canyon deeper with every single drop. A glacier is quietly grinding an entire mountain into dust. And we just live here, completely unbothered, arguing about what to watch tonight. Earth is not a finished product. It is not a postcard or a screensaver. It is the most chaotic, dramatic, restless construction site in the solar system. And every single landscape you have ever seen is just a snapshot of something that is still happening. Water versus rock, fire versus ice, time versus literally everything. The planet never stops, never sleeps, never gets tired of making something more insane than the last thing. In this series, we're going to travel through the wildest, weirdest, most unbelievable places this world has ever built. No filters, no CGI, just the raw, ridiculous creativity of nature doing its thing. Before we dive in, drop a comment below. Where are you watching from right now? Seriously, I want to know. Let's see just how far around this planet we actually reach. Let's go. Let's talk about something that most people never think about, which is the fact that the planet you're standing on is hollow in places. Not in the science fiction, lost world kind of way, though if you squint the reality is not too far off. Beneath your feet, right now, there are passages and chambers and vaulted halls that have been carved out over millions of years by the quietest, most patient force on Earth. Not lava, not earthquakes, not some dramatic tectonic collision. Water. Just water, moving slowly, dissolving rock one microscopic layer at a time, building entire underground worlds without any apparent plan or ambition, other than finding the lowest possible point to settle. Water is, in geological terms, extraordinarily determined. This is the chapter about what happens when that determination gets left alone for a very long time. To understand how a cave forms, you need to briefly appreciate just how sneaky water actually is. When rainwater falls through the atmosphere, it picks up carbon dioxide and becomes a weak carbonic acid. Not the kind of acid that burns through metal in action movies, but the kind that, given a few thousand years, will quietly eat through limestone like a slow and methodical diner working through an enormous meal. The water finds a crack in the rock, widens it, finds another crack, widens that too, and gradually the whole underground structure starts to open up. It is, geologically speaking, almost boring in its simplicity, and yet the results are anything but boring. The caves of Waitomo in New Zealand are perhaps the most dramatic example of how nature turns an otherwise unremarkable process into something that looks like it was designed for a theatrical production. Waitomo sits in the Waikato region of the North Island, an area that on the surface looks fairly ordinary. Rolling green farmland, limestone outcroppings, the kind of scenery that makes you think pleasant and uncomplicated thoughts. Then you go underground, and all previous conceptions of what a cave should look like are immediately and permanently revised. The cave system at Waitomo has been forming for roughly 30 million years. The limestone that makes up its walls was once the floor of a shallow tropical sea, and the fossils of ancient marine creatures are still embedded in the rock if you look closely. Over millions of years, as the land slowly rose and water found its way through, the passages opened and the chambers grew. By the time the first Maori explorers descended into these caves sometime in the 19th century, the underground architecture had reached a level of complexity that would take a team of engineers years to map. The guide who first brought European visitors into the caves in the 1880s was a local chief named Tain Tinarau, who'd been exploring the system by candlelight for years with his wife. They had figured out, among other things, that the cave system connected to a river entrance further downstream, which is still how visitors enter today, floating silently through the dark on small boats. Tain Tinarau, it should be noted, was also eventually appointed the official caretaker of the caves by the government, which represents an unusually satisfying historical outcome compared to the way such stories often end. But the cave's fame does not come from the limestone formations. Impressive as those are, it comes from the ceiling. The moment your eyes adjust to the darkness inside Waitomo's glowworm grotto, you understand immediately why every description of this place eventually runs out of adequate vocabulary. The ceiling is covered in light, thousands of tiny blue-green points of luminescence, dense as the Milky Way on a perfectly clear night, stretching across the rock in patterns that feel simultaneously random and organized. You are, in effect, lying at the bottom of the ocean looking up at the stars, except the stars are alive and they are hungry, and they are significantly less romantic than they look. The light comes from the larvae of a fungus gnat called Arachnocampa luminosa, a species found nowhere else on Earth. These are, technically speaking, glowworms, though that name does them considerably more credit than they perhaps deserve on a personal level. Each larva hangs from the ceiling in a nest of mucus, and yes, it is exactly as appealing as it sounds, and suspends dozens of sticky silk threads below it, anywhere from 10 to 70 threads per larva, each thread beaded with tiny droplets of mucilage. The glowworm produces its light from a chemical reaction in a specialized organ at the tip of its abdomen, a bioluminescent process that has nothing to do with magic and everything to do with biochemistry. The light attracts other insects flying through the cave, which crash into the sticky threads, get pulled up and become dinner. The whole operation is quietly ruthless. The ceiling of the glowworm grotto is, when you think about it, the world's most beautiful insect trap, and the hundreds of thousands of tourists who float beneath it every year are essentially watching a very slow, very pretty hunting scenario. This does not make it any less astonishing. If anything, it makes it more so. What is particularly remarkable about Arachnocampa luminosa is how precisely it controls its light output. When food is plentiful, the larvae glow more brightly, presumably because they can afford to burn the energy. When they are hungry, the light intensifies further, a kind of desperate advertising. When disturbed or threatened, the light dims almost immediately, which is why the boats through the grotto travel in complete silence. The guides do not speak above a whisper. The tourists are asked not to use camera flashes, and in that enforced quiet, floating through absolute darkness beneath the ceiling of a living light, even the most enthusiastic smartphone user tends to put their phone away and simply look. The caves have a way of insisting on proper attention. The limestone formations at Waitomo are also worth noting, even if they inevitably play second fiddle to the ceiling show. Stalactites and stalagmites form when water-carrying dissolved calcium carbonate drips from the ceiling, deposits a tiny amount of mineral as the carbon dioxide escapes into the cave air, and repeats this process for centuries. A stalactite grows from the ceiling downward, a stalagmite rises from the floor upward, and when they eventually meet, a process that can take tens of thousands of years, they form a column. Geologists have a useful mnemonic for remembering which is which. Stalactites hang tight to the ceiling, stalagmites might reach the roof one day. This mnemonic is taught to every geology student and approximately half of all cave tour visitors, which means it has probably been repeated more times than most national anthems. It is, however, effective. The average stalactite grows about 1 centimetre every 100 years, which puts the ambitions of human infrastructure projects in a somewhat humbling perspective. Waitomo contains examples of another formation category called helictites, which are among the stranger objects you will encounter in a cave environment. Unlike stalactites, which follow gravity straight downward, helictites grow sideways, upward, in spirals, in curves, in directions that have no apparent relationship to the laws of physics as you have been taught them. They look like frozen white coral, or the sketch a particularly caffeinated architect might produce at 2 a.m. The explanation for their bizarre growth patterns involves internal fluid pressure, impurities in the water, and the precise crystalline structure of calcite, none of which is especially satisfying as an explanation because the visual result continues to look like someone cheated. Nature, as a general rule, is not especially interested in making its mechanisms look plausible. If Waitomo represents water working patiently over millions of years through relatively soft limestone, the marble caves of Lake General Carrera in Patagonia represent something slightly different. Water working for 6,000 years against something considerably harder, and winning anyway. The lake sits on the border between Chile and Argentina, in a region so remote that most maps of South America conveniently omit it at standard zoom levels. The lake itself is vast, one of the largest in South America, spanning nearly 2,000 square kilometers, and its water is an extraordinary pale turquoise blue, the color of glacial meltwater, which is precisely what feeds it. The surrounding mountains are covered in ice fields, and for thousands of years glacial runoff has been pouring into the lake and slowly, very slowly, doing something extraordinary to its western shore. Along that shoreline, a peninsula of solid marble extends into the water. Marble, for context, is metamorphic limestone. Limestone that has been subjected to intense heat and pressure underground, until it recrystallizes into something harder and more compact. It is the material of classical sculpture, of ancient temples, of the Taj Mahal's exterior. It is not, generally speaking, the kind of thing you expect water to casually rearrange. And yet the glacial water of Lake General Carrera has done exactly that, dissolving and smoothing and carving the marble over 6 millennia, until the shore has become a series of caverns, tunnels, columns, and arched ceilings of pure calcite, their surfaces swirling with greys and whites and pinks in patterns that look genuinely hand-painted. The local name for the formation is Capillas de Marmol, the Marble Chapels, and the name is more accurate than most geographical designations manage to be. The caves are accessible only by boat, which is, if you're making the journey, something to plan for in some detail. The nearest town of any significant size is Chile Chico, a community of a few thousand people on the Chilean side of the lake, and the roads connecting it to the rest of the continent are the kind that feature prominently in travel memoirs of the adversarial variety. The famous Carretera Austral, Chile's southern highway, runs through this region, and sections of it in the early 2000s were still unpaved gravel roads prone to becoming impassable in rain. The journey from Santiago, Chile's capital, to the lake was, for most of the 20th century, an undertaking measured in days rather than hours. This remoteness is a large part of why the caves remained largely unknown outside Patagonia until relatively recently, and it is also why the water has had 6,000 years to work in peace without anyone particularly bothering it. What makes the marble caves visually extraordinary, beyond the obvious fact that they are polished chambers of stone naturally decorated with patterns of breathtaking complexity, is the relationship between the rock and the water's colour. The turquoise of the glacial lake is not static. It shifts depending on the season and the snowmelt levels, ranging from a pale aquamarine in winter to a deeper, almost electric blue-green in summer when the melt is at its peak. Because the cave walls and ceilings are highly polished marble, they act as mirrors, reflecting the water's colour back up through the cavern. When the light is right, generally late morning on a calm day, when the sun is at an angle that sends shafts directly into the cave openings, the entire interior of the marble chambers glows with the reflected turquoise of the lake below. The walls appear to pulse with colour. The ceiling seems to be underwater. The whole environment produces a quality of light that painters have been chasing since there were painters, which is to say a very long time, and which nature appears to have achieved here without any formal training. The marble itself carries a record of the geological violence that created it. The swirling grey and white veins in the stone are traces of different mineral compositions, laid down when the original limestone was squeezed and heated underground around 300 million years ago. The pink tones come from iron oxide. The darker inclusions are older rock caught up in the metamorphic process and compressed into the marble matrix. Each pattern on the cave wall is, in effect, a geological timeline, a compressed history of the Earth's interior written in mineral pigment across what is now one of the most otherworldly tourist destinations on the planet. You are quite literally looking at time itself when you look at the marble caves, which is a thought that tends to produce either profound reflection or a slightly dizzy feeling, depending on your constitution. It is worth pausing here to appreciate the sheer improbability of these places existing at all. The Waitomo caves required a specific type of limestone, deposited at a specific time, uplifted at a specific rate, and then exposed to the precise chemical and hydrological conditions that allowed both the cave system and the glowworm colony to develop. The marble caves required an ancient seabed to become metamorphic rock, that rock to be exposed by tectonic activity, glacial meltwater to exist nearby, and 6,000 years of undisturbed erosion. Change any one of those variables and the result is a different cave, or no cave at all, or a cave with an entirely different ceiling that does not glow at night. The planet builds these things with no particular intention, and yet when you encounter them, the sensation is powerfully of design, of intention, of something that was meant to be seen. That sensation is, itself, one of the more interesting things about being a conscious creature living on a geological one. There are caves on every continent, and each major system has its own character. The Sun Dung Cave in Vietnam, discovered by locals in 1991 and mapped by British cavers in 2009, is the largest known cave passage on Earth, large enough to contain a full-size jungle inside it, which it does, including its own weather system, and a cloud layer that forms near the ceiling when the temperature differential is right. The cave is so large and so remote that a full expedition to reach its deeper sections requires several days of hiking, specialized equipment, and a reasonable tolerance for the kind of darkness that has no bottom. The jungle inside Sondung exists because two sections of the cave ceiling have collapsed, creating skylights large enough to let in sufficient sunlight for trees to grow up to 30 meters tall. There are sinkholes within the cave floor. There are rivers. There are ecosystems that developed in complete isolation. Sondung is, in effect, a world inside a world, which sounds like a sentence from a fantasy novel, but is simply a geological description. The reed flute cave in Guilin, China, has been visited by humans for at least 1,200 years. Inscriptions on its walls from Tang Dynasty visitors are still legible, making it one of the longer-running tourist attractions on record. The cave gets its name from the reeds that grow at its entrance, and were historically cut to make musical instruments, which is the kind of incidental detail that makes a place feel genuinely connected to human life, rather than merely spectacular. Inside, the calcium carbonate formations have been given names by centuries of visitors: the Crystal Palace, the Dragon Pagoda, the Flower and Fruit Mountain. The names are not subtle, but they are accurate. The stalactites and columns in Reed Flute Cave have grown into configurations so elaborate that in some chambers they resemble nothing so much as the interior of an enormous cathedral organ. If someone had built it out of translucent white mineral over the course of 400 million years, which is approximately how old the limestone here is. The Hang Sondung discovery story is worth a moment's attention because it illustrates something about the relationship between local knowledge and formal scientific documentation that tends to get underplayed in the narrative of cave exploration. Ho Khan, the local man who first stumbled upon the entrance to Sondung in 1991, was a forest worker from the region who regularly travelled through the dense jungle of the Phonghakebang area, looking for timber and wildlife. He found the cave entrance by accident when he heard the sound of a river and felt a strong wind rising from the ground, both classic signs of a large underground passage. He went part way in, noted the size of the opening, and then left because a storm was coming. He could not find it again for several years afterward. The jungle in that region is not the kind of place where landmarks stay obvious. When he finally relocated it in 2008 and brought British cavers from the Cave Research Group to the site, what they found inside required weeks of exploration to begin to comprehend. The cave's main passage is roughly 5 kilometers long, up to 200 meters wide, and in places over 200 meters tall. The caving team's survey equipment initially malfunctioned because the scale of the space was outside the parameters it had been designed to measure. This is the kind of problem that qualifies as a good problem to have, strictly speaking. Underground rivers, the forces that created many of these cave systems, are among the least understood hydrological features on Earth. A river above ground follows visible topography, and its behaviour, while sometimes surprising, operates according to observable gradients and banks. An underground river has none of these courtesies. It follows the path of least resistance through the rock, which is rarely a straight line, and it can disappear into one crack and emerge from an entirely different crack 5 kilometers away with no obvious surface connection. The underground rivers of the Yucatan Peninsula in Mexico, for example, move through a vast network of flooded cave passages called cenotes, some of which connect to the open sea. Mayan civilization used these cenotes as water sources, ceremonial sites, and in some cases as places of offering. Archaeologists have recovered remarkable quantities of material from their depths, including objects that were clearly placed there deliberately rather than dropped accidentally. The cenotes are, in their own way, a record of human engagement with underground water that spans several thousand years, which gives them a different kind of depth than the purely geological. Back at the surface of this underground world, it is worth considering what caves have meant to human beings over the long stretch of history in which we have been finding them and deciding what to do with them. The oldest known cave paintings are in the Chauvet Cave in France, dated to roughly 37,000 years ago. The people who made them were anatomically modern humans, fully as intelligent and creative as anyone living today, navigating deep into the rock by firelight and painting horses, rhinoceroses, lions and bears on the walls with a skill and confidence that continues to impress art historians. What motivated them to go so far underground to make art is not entirely clear. The entrance areas of many ancient painted caves show no sign of long-term habitation. People did not live in these deeper chambers. They went in, made the paintings, and came out. The caves were, for something. Whether that something was ceremonial, religious, communicative, or some combination of purposes we no longer have a framework for understanding, we cannot say with certainty. What we can say is that the instinct to enter these underground spaces and do something meaningful in them appears to be a very old instinct indeed. The stalactites in Chauvet Cave were photographed during the original survey of the site in 1994, and several of them had been deliberately moved and rearranged by the ancient visitors, placed upright, leaned against walls, positioned in ways that served no obvious structural purpose. Someone, 37,000 years ago, picked up pieces of cave formation and arranged them. Whether this was play or art or ritual, or simply someone keeping themselves busy while they waited for something else to happen underground, is a question that no amount of scientific analysis has managed to definitively resolve. The caves keep their secrets with considerable thoroughness. What water creates underground is, in one sense, simply the logical result of chemistry. Acid meets mineral, mineral dissolves, space opens, process continues. But the end results, the glowing ceiling of Waitomo, the colour-washed marble of Patagonia, the jungle-containing vastness of Sondung, are so far removed from the mechanical simplicity of the process that they feel like category errors, like something that should not have been produced by chemistry alone. This gap between the plainness of the cause and the extravagance of the effect is perhaps one of the defining characteristics of natural processes in general. The universe is, it turns out, very good at building extraordinary things out of very ordinary materials, and water has been one of its most reliable tools for the entire history of the planet. This is worth keeping in mind as we move from what water does underground to what it does when given a completely flat, open surface and an unlimited sky above it. The Salar de Uyuni in Bolivia is, at roughly 10,500 square kilometers, the largest salt flat on Earth. It sits in the southwest of the country at an altitude of about 3,600 meters on the Altiplano, the high plateau shared between Bolivia, Peru, Chile and Argentina, a landscape of extreme weather, thin air, and a quality of light that photographers describe using words like brutal and divine, often in the same sentence. The Salar was, somewhere between 40,000 and 25,000 years ago, part of a vast prehistoric lake called Lake Minchin, which covered much of the Altiplano and was, by any modern standard, an inland sea of considerable ambition. As the climate shifted and the lake evaporated over thousands of years, it left behind a thick crust of salt and mineral deposits across the flat basin floor. The depth of that salt crust varies across the Salar, but averages around 10 meters in the center, which works out to an estimated 10 billion tons of salt in total. Bolivia, which consumes around 25,000 tons of salt per year domestically, has not yet found it necessary to mine the Salar de Uyuni with any particular urgency, which is probably wise. For most of the year, the Salar is exactly what its name suggests, a vast, dazzlingly white flat expanse of hexagonal salt tiles, cracked into geometric patterns by the heat and the alternating cycles of dryness and light rain. The hexagonal cracking is the same phenomenon that produces similar patterns in dried mud and in basalt columns like the Giant's Causeway in Northern Ireland, a result of the physics of how surfaces contract under specific conditions. We will return to geometric patterns in nature later in this series because they are genuinely extraordinary. But the hexagonal salt crust of Uyuni deserves its own acknowledgement here. The tiles range in diameter from roughly 30 centimeters to over 2 meters, and their edges curl slightly upward, giving the surface an almost tiled appearance that somehow manages to look deliberate, as if someone had laid a ceramic floor across an area roughly the size of Jamaica, and then walked away without signing their work. During the rainy season, which runs from November to March, the situation changes in a manner that has made the Salar de Uyuni one of the most photographed landscapes on the planet. Rainfall on the Altiplano is rare and often light, but the flat basin has nowhere for water to drain, and even a thin layer of standing water, sometimes just a few centimeters deep, transforms the salt flat into a perfect mirror. The water is too shallow to have any wave action of significance. It is, in effect, a horizontal pane of glass across 10,000 square kilometers of perfectly flat surface, and it reflects the sky with a clarity and completeness that defies description in straightforward terms. On a clear day with good clouds, the horizon disappears entirely. The ground and the sky become one continuous image. People standing on the salt flat appear to be standing in the middle of the clouds. The distinction between up and down, between earth and atmosphere, is not just blurred, it is completely erased. The photographs look to anyone who has not visited like they have been manipulated in post-production, and the defense of the photographers in question is that no manipulation was necessary because the landscape was already doing all the work. There is something almost philosophically unsettling about the Salar de Uyuni's mirror effect, beyond the simple visual drama of it. The brain's entire system for understanding spatial orientation depends on the reliable assumption that the ground is below and the skies above, and that the horizon separates them. Remove that assumption, as the sailor does when it mirrors, and a persistent low-grade disorientation sets in that no amount of intellectual understanding quite resolves. Visitors report feeling, despite knowing perfectly well where they are, a sensation of groundlessness, as if the surface they're walking on might not be entirely trustworthy. This is what happens when a landscape successfully dismantles one of your most basic sensory assumptions. The altiplano altitude, 3,600 meters, where the air contains roughly 2/3 the oxygen of sea level, does not help the overall feeling of groundedness. The Salar is, in short, a beautifully destabilizing place, which is probably why people keep going back. The wildlife of the Salar de Uyuni is an unlikely highlight of any visit, partly because the landscape itself is so extreme that the existence of wildlife seems almost defiant. 3 species of flamingo breed here: the Andean, the Chilean, and the James flamingo, gathering in their thousands around the edges of the shallow lagoons that dot the Salar's periphery. The flamingos feed on algae and diatoms in the saline water, which contain the carotenoid pigments that give the birds their pink colouring. Without these pigments in their diet, flamingos are actually white. So a flamingo's colour is essentially an edible autobiography, a visible record of what it has been eating, which is either a charming idea or a deeply uncomfortable one depending on how you feel about dietary transparency. The flamingos of Uyuni nest at altitudes of up to 4,600 meters, making them among the highest altitude nesting birds on Earth, and they appear entirely untroubled by the cold, the wind, the thin air, and the occasional tourist trying to photograph them from a modified Toyota Land Cruiser. Flamingos, as a species, project an air of magnificent indifference to human attention that most people find either admirable or slightly offensive. The Salar also sits above one of the world's largest reserves of lithium, a metal that has become critically important for battery technology in electric vehicles and electronic devices. Roughly half the world's known lithium reserves are concentrated in the lithium triangle of Bolivia, Chile and Argentina, with the Bolivian deposits largely under the Salar de Uyuni. The tension between the economic value of these deposits and the environmental importance of the Salar as a tourist destination, an ecosystem, and a UNESCO candidate site has been a source of significant political and environmental debate in Bolivia for decades. The question of how to extract lithium without destroying the landscape that sits above it is, to put it diplomatically, not yet resolved. The salt flat continues to do its mirror impression, unaware of and entirely unconcerned by the geopolitical conversations happening around it. The Salar de Atacama in Chile, smaller than Uyuni but no less extreme, produces a different kind of visual drama. The water that collects in its salt pools is not the clear, sky-reflecting shallow layer of the Bolivian Salar, but a briny, mineral-saturated liquid that sits in deep pink and red tones, where microorganisms, principally halophilic algae and bacteria, colour the water from within. The flamingo populations here are similarly enormous, and the visual combination of deep pink water, white salt crust and the snow-capped Atacama volcanoes in the background produces a landscape that a reasonable person might describe as maximalist, in a geological sense. But if the Salar de Uyuni represents water as a mirror, passive, reflective, elegant, then Lake Natron in Tanzania represents water as something considerably less hospitable. Natron sits in the Gregory Rift in northern Tanzania, at the edge of a volcanic zone where the East African rift system is slowly, very slowly, tearing the continent apart. The lake is fed by mineral-rich hot springs, and the combination of volcanic geology, intense evaporation in the hot East African sun, and the particular chemistry of the incoming water has produced a body of water with a pH level between 9 and 10.5, roughly equivalent to household ammonia. The water is not merely alkaline, it is caustic enough to cause chemical burns on unprotected skin. It is not, to state the obvious, a lake you would choose for recreational swimming. What gives Natron its most striking visual quality is its colour. The high alkalinity of the water supports the growth of cyanobacteria and haloarchaea, microorganisms that produce red and orange pigments called carotenoids and bacterioruberin. During the hot season, when evaporation concentrates the lake's chemistry to its most extreme levels, the water turns a deep blood red or burnt orange across much of its surface. Viewed from above, the lake looks like something has been poured into the landscape by someone with very specific aesthetic intentions. It is beautiful in the same slightly alarming way that other genuinely dangerous things can be beautiful. The visual appeal and the practical threat operating simultaneously, with no contradiction between them. The calcified remains of birds and animals found along Natron's shoreline became famous after photographer Nick Brandt documented them in 2013 with a series of images that circulated widely online and produced a significant amount of alarmed commentary. The photographs showed flamingos, swallows, and other birds apparently turned to stone, their bodies preserved in calcium carbonate and sodium carbonate deposits in postures that suggested they had simply stopped mid-movement. The images were striking enough that several media outlets described the lake as instantly killing animals and turning them to stone, which is somewhat more dramatic than the actual process. What Natron does is preserve. Animals that die in the lake, from exhaustion, disorientation, or simply the effects of the alkaline water on skin and mucous membranes, are encased in the mineral deposits of the lake's crust as the water evaporates, which preserves them in postures of extraordinary naturalistic detail. They do not turn to stone instantly, but the end result in photographs is genuinely eerie. A bird perfectly rendered in calcium carbonate, extended wings frozen, eyes mineralized, looking as if it landed 5 minutes ago and has simply not moved yet. The flamingos, however, are not deterred. An estimated 2.5 million lesser flamingos use Lake Natron as their primary breeding ground in the East African Rift System. They nest on the salt crust in the shallow areas of the lake, where the extreme chemistry of the water keeps terrestrial predators away. Most land animals cannot tolerate sustained contact with the lake's surface and edges. The flamingos have evolved specific adaptations that allow them to breed in this environment. Their skin is tougher than that of most birds. Their legs develop thick calcium carbonate casings that insulate them from the caustic water, and their chicks are able to walk on the salt crust within days of hatching. The lake that preserves dead animals in mineral is also the breeding ground for millions of living ones. Natron is, in this sense, a place of simultaneous death and prolific life, which nature seems entirely comfortable with even if the optics are a bit confusing for visiting observers. The hot springs that feed Lake Natron are part of the broader volcanic activity of the Rift System, and the same hydrothermal forces that produce Natron's chemistry are responsible for the spectacular volcanic landscapes of the surrounding area, including Oldoño Lengai, an active volcano visible from the lake's shore that erupts with a type of lava found nowhere else on Earth. Carbonatite lava, the kind Lengai produces, is the coldest known lava on the planet, erupting at around 500 degrees Celsius compared to the more typical basaltic lava temperatures of over 1,000 degrees. It is also extraordinarily fluid, flowing almost like water at times, and it begins to weather and disintegrate almost immediately on contact with the atmosphere, turning from jet black to pale grey within hours and eventually dissolving in rain. Lengai's unusual lava is connected to the same carbon dioxide-rich geology that makes Natron what it is, and together the volcano and the lake form one of the more chemically extreme environments in the East African landscape. Visiting geologists tend to describe the whole region with a kind of professional enthusiasm that borders on giddy, which is reassuring to know even if it does not entirely resolve the question of whether to wear protective footwear near the water's edge. The idea that connects the Salar de Uyuni and Lake Natron, despite their apparent differences, is that both are places where water's behaviour is defined not by its usual role as a neutral carrier of life, but by its chemistry, by what it contains. The salt and the alkalinity change everything. The colour, the physics, the biology, the entire relationship between the water and the organisms that try to live in it. Water, it turns out, is not a single thing. It is a spectrum, and at the extremes of that spectrum it produces environments that challenge every comfortable assumption about what a body of water is supposed to look like and do. One reflects the sky with perfect fidelity. The other turns animals into mineral monuments. Both are, in their own way, examples of water showing off. And if there is a through line connecting this entire chapter, the glowworm caves, the marble chapels, the blinding salt flat, the red lake of Tanzania, it is this. None of these places are decorations. None of them exist to be looked at. They are the visible surfaces of enormous, ongoing, entirely indifferent processes, and what we interpret as beauty is simply the side effect of chemistry and physics and time doing what they were always going to do. The planet did not carve the marble caves to produce a tourist destination. Water did not cover the Bolivian altiplano with a reflective skin to produce a photograph. The glowworms did not light up their cave ceiling to provide atmosphere. They are all simply doing what their chemistry demands, in the places their geology provides, with a thoroughness and consistency that spans timescales we are barely equipped to imagine. That we find the results beautiful is, in the end, our problem, and a remarkably pleasant one to have. If water is the patient sculptor of the underground world, then fire is its impatient counterpart on the surface. And when we talk about volcanoes, we are not talking about destruction in the way that word usually gets applied to them. The eruption footage, the evacuations, the dramatic before and after satellite comparisons, all of that exists, and none of it is inaccurate. But it is incomplete. Volcanoes are not just forces of demolition. They are, on the longest timescale that matters, the primary construction workers of this planet. Every continent, every island, every mountain range with volcanic origins exists because the Earth's interior is hot enough to melt rock, and occasionally, with considerable enthusiasm, push that melted rock toward the surface. Without volcanism, there would be no Hawaii, there would be no Iceland, there would be no Japan, no Kamchatka, no Cascade Range. There would, in all likelihood, be no breathable atmosphere, because the early volcanic outgassing of the young Earth is what produced most of the gases that eventually became the air we are currently using. Volcanoes, in the most literal sense possible, built the place. The fact that they occasionally also destroy parts of it is, from a geological perspective, a relatively minor footnote. The three volcanoes worth examining in this chapter each illustrate a completely different way the Earth decides to rewrite its own landscape, and they do so with a variety of personality that makes the general category of volcano considerably more interesting than the standard eruption narrative would suggest. The story of Paracutine is, on its surface, the most improbable thing in this entire series, and given that this series includes a cave full of bioluminescent larvae and a lake that turns animals into mineral sculptures, that is saying something. On February 20th, 1943, a farmer named Dionisio Pulido was working in his cornfield in the Mexican state of Michoacán, doing the kinds of things that farmers do in cornfields in February, when the ground near a small depression in the field began to hiss. Then it began to smoke. Then it began to crack. Pulido reportedly tried to fill the crack with soil, which is either the bravest or the most optimistic agricultural decision in recorded history, and was predictably unsuccessful. By the next morning, the crack had become a cone several meters high, ejecting rock and ash. Within a week, the cone was over 100 meters tall. A new volcano had been born, in the middle of a cornfield, while the farmer who owned the cornfield watched. Paracutine is classified as a monogenetic cinder cone, which is a type of volcano that erupts from a single vent, builds up a cone of ejected material, and typically erupts for a geologically brief period before going quiet. Cinder cones are the most common type of volcano on Earth, though they are also the most modest in terms of individual scale. What made Paracutine extraordinary was not its eventual size. It grew to 424 meters over 9 years of activity, which is impressive for a cinder cone but not catastrophic by volcanic standards. But the fact that its entire lifespan was observed by humans from the very first moment. Most volcanoes that geologists study either have already erupted and been quiet for centuries, or are ancient systems so large and complex that their activity can only be understood statistically. Paracutine was born in front of witnesses and grew up under continuous scientific observation. It was, for volcanologists of the 1940s and 1950s, the equivalent of a controlled experiment that nobody had set up and nobody was controlling, which made it both scientifically invaluable and epistemologically slightly humbling. The lava flows from Paracutine were predominantly basaltic, slow-moving, thick, and relentless. They did not travel at dangerous speeds. They advanced, generally, at the pace of a determined person walking with purpose, which is roughly 3 to 4 kilometers per hour when the flow is fresh and hot, slowing considerably as it cools and stiffens at the margins. The nearby village of San Juan Parangaricutiro was engulfed over several months between 1944 and 1946, with the lava moving slowly enough that residents had time to remove their possessions and in some cases dismantle parts of their homes before the flow arrived. The church of San Juan, built in the 16th century, was swallowed to its rooftop. Today, the tower of the church and the top of the facade protrude from the hardened lava field, a sight that visitors still make the journey to see. It is, as visual metaphors go, quite a strong one. A centuries-old church slowly engulfed by something considerably older than it. The lava was not particularly concerned with relative age. By 1952, Paracutin had gone quiet. Its 9-year eruption had produced a cone, a lava field covering roughly 25 square kilometres, and the complete burial of 2 villages, but no fatalities directly from the lava itself. 3 people died during the eruption, all from lightning strikes associated with the volcanic activity, which is a detail that raises questions we will address shortly. The corn farmer Dionisio Pulido, whose field was the birthplace of a mountain, was relocated to a nearby town, along with the rest of the displaced population. He reportedly remained philosophical about the whole experience, which seems like a reasonable response to having a volcano grow out of your agricultural land. The ground around Paracutin remains volcanically active at low levels, and the broader Michoacán-Guanajuato volcanic field that produced it contains nearly 1,400 documented vents from past eruptions, scattered across the landscape at irregular intervals. In geological terms, the field is still capable of producing new vents. The next Paracutin, if there is one, could appear anywhere within that field, with the same approximate warning that Dionisio Pulido received, which is to say, a hissing sound and a crack in the earth, followed by events moving rather quickly. Local geological monitoring has improved considerably since 1943, which is reassuring, though it does not fundamentally change the situation of living in a region where volcanoes can appear in previously unremarkable locations. The people of Michoacán are, as a matter of practical necessity, comfortable with this uncertainty in a way that residents of most other places are not. Kilauea on the Big Island of Hawaii operates on an entirely different principle, and understanding it requires a brief explanation of why Hawaii exists at all, which is itself one of the more counterintuitive stories in geology. The Hawaiian Islands are not located at a tectonic plate boundary, which is where most volcanic activity on Earth occurs. They sit in the middle of the Pacific Plate, far from any boundary, and they exist because of a hotspot, a plume of abnormally hot mantle material that rises through the Earth's interior from deep below and melts through whatever plate happens to be above it. The Pacific Plate moves northwest at roughly 8 centimeters per year. The hotspot stays fixed. The result is a chain of volcanic islands, each one younger than the one to its northwest, recording the plate's movement like a geological timestamp sequence. The Big Island, where Kilauea sits, is the youngest and southernmost, and it is still directly over the hotspot. The older islands, Maui, Molokai, Oahu, Kauai, have been carried away from the hotspot and are no longer actively building themselves up. Further along the chain, past Kauai, the islands become atolls, then seamounts, then disappear below the waterline entirely, gradually ground down by erosion faster than they are being built up by volcanism. The Hawaiian chain is a moving record of the Pacific Plate's journey, and Kilauea is currently writing the latest chapter. What distinguishes Kilauea from Paracutin is longevity. Where Paracutin erupted for 9 years and stopped, Kilauea has been in essentially continuous eruption for most of the last several million years. The eruption that began in 1983 on Kilauea's East Rift Zone lasted until 2018. 35 years of uninterrupted lava production from the Pu'o'o vent complex, during which roughly 2 billion cubic meters of lava were erupted, and roughly 125 square kilometers of new land were added to the island of Hawaii. The eruption ended somewhat abruptly in 2018, when a series of new fissures opened in a residential area called Leilani Estates, and the supply of magma that had been feeding Pu'u'o'o was redirected. The resulting eruption in the lower East Rift Zone destroyed over 700 homes in a matter of weeks, which is a reminder that volcanoes, however patient they may appear in their gentler moments, are not obligated to give extended notice. The lava that Kilauea produces when it flows into the ocean creates new land in a process that is, visually, one of the more dramatic things the planet does in what might loosely be called real time. Molten basalt at roughly 1100 degrees Celsius contacts seawater, and the results are immediate and violent. Clouds of superheated steam called lays rise in dense white columns. The lava surface cools and shatters into fragments, and a delta of new volcanic rock gradually extends the coastline into the sea. The lays plumes contain hydrochloric acid and tiny glass particles, and are not safe to breathe, which is why the viewing areas for this phenomenon are kept at a respectful distance. The new land that forms is initially unstable. The deltas can collapse without warning into the ocean, but over time it consolidates into bench formations that become permanent additions to the island's coastline. Standing at the edge of an active lava delta and watching the coastline of an island extend itself into the ocean is, by most accounts, an experience that recalibrates one's sense of geological timescales in a way that no classroom description quite manages. You're watching an island being built, not in a metaphorical sense. You're watching an island be physically larger than it was yesterday. Kilauea's summit caldera, Halema Umau, has contained an active lava lake at various points in its recent history, including a spectacularly large and active lake that formed in 2008 and persisted for a decade, visible as a glow above the crater at night from several kilometers away. The Pele connection, the Hawaiian goddess of volcanoes, storms and fire traditionally associated with Halema Umau, gives the cultural dimension of Kilauea a continuity that is unusual among the world's volcanic systems. Hawaiian oral tradition has tracked the activity of Kilauea's caldera for centuries, and the traditional accounts of Pele's movements across the islands are, when mapped against the geological record, surprisingly consistent with the actual direction of volcanic migration through the island chain over time. Whether this represents systematic observation recorded mythologically, extraordinary coincidence, or some combination of both is a question that different scholars approach with different degrees of enthusiasm. The volcano itself continues erupting regardless of how humans decide to contextualize it. Volcán de Fuego in Guatemala presents a third personality entirely. Where Paricutin was a birth and Kilauea is a long, steady construction project, Fuego is something closer to a perpetual state of agitation. Fuego, the name means simply fire, which is accurate if not especially inventive, sits in the highlands of Guatemala alongside two companion volcanoes, Acatenango and Agua, all three visible from the colonial city of Antigua below. Fuego is one of the most consistently active volcanoes in Central America, erupting in some form several times per year, and it has been in a more or less continuous state of minor to moderate activity since at least the 16th century, when Spanish colonial records began documenting it. The local indigenous communities of the region had, of course, been observing and living with it considerably longer. What Fuego is particularly known for, among those who study explosive volcanism, is the generation of volcanic lightning, one of the most visually extraordinary phenomena in the entire catalogue of natural events. When Fuego produces a significant eruption column, the massive volume of ash, rock fragments, and gas rising into the atmosphere creates an environment of intense electrical activity. The particles collide, separate, collide again, and in doing so generate static charge in quantities sufficient to produce lightning within the eruption column itself. These are not ordinary lightning bolts. They are shorter, more chaotic, and they emerge from within the ash cloud rather than from standard cumulonimbus formations above, creating images that look, to anyone accustomed to ordinary weather photography, fundamentally wrong, as if someone has added special effects to a photograph of a volcanic eruption that did not need them. The bolts are often purple or blue-white, brighter and more compact than regular cloud-to-ground lightning, and they illuminate the ash plume from within in ways that produce a strobing, flickering quality unlike anything in standard storm photography. The mechanism behind volcanic lightning involves several competing theories: triboelectric charging from particle collisions, ice formation in the upper eruption column producing charge separation similar to ordinary thunderstorm processes, and fract emission from the shattering of rock and glass particles. In reality, all three processes probably contribute to different types of lightning seen in different parts of an eruption column and at different stages of an eruption. What volcanologists have established through high-speed cameras and electromagnetic sensors is that volcanic lightning begins within the first seconds of a significant eruption, which puts it among the fastest electrical events associated with volcanic activity. The charge builds and discharges almost simultaneously with the eruption itself, which suggests a direct mechanical relationship between the violence of the explosion and the electrical activity it generates. The volcano is, in a very literal sense, generating its own weather. It is producing a storm inside a storm which seems, even by the standards of everything else in this series, fairly ambitious. The eruption of Fuego in June 2018, the same year as Kilauea's major lower rift eruption, was catastrophically violent, producing pyroclastic flows, fast-moving avalanches of hot gas and volcanic material that travelled down the mountain's flanks at speeds of up to 400 km per hour. The eruption killed more than 400 people in surrounding villages, making it the deadliest eruption in Guatemala in a century. The speed and direction of the pyroclastic flows were partly unexpected based on Fuego's previous behavior patterns, which is a reminder that even well-monitored volcanoes retain the capacity to behave outside of their established parameters. Fuego continues to erupt regularly since then. The communities on its lower flanks continue to live there, partly from economic necessity, partly from generational attachment to the land, and partly because the volcanic soil on the slopes of Fuego is extraordinarily fertile. The same minerals that make volcanic environments geologically dangerous make them agriculturally productive, a trade-off that has defined human settlement near active volcanoes for as long as humans have been settling near anything. The fertility of volcanic soil is not incidental to this chapter's broader argument. Volcanoes build land, yes, but they also build the conditions for biological complexity. The basalt that Kilauea pours into the ocean will, over centuries, weather into mineral-rich soil that supports native Hawaiian plant species. The ash that Fuego deposits across Guatemala's highlands replenishes mineral content that agriculture gradually depletes. The obsidian produced by volcanic cooling was one of humanity's first tools, valued for the sharpness of its edges by cultures across Central America, Anatolia, and the Pacific Islands long before metalworking developed. The connection between volcanic geology and human civilization is not just the dramatic story of Pompeii, though Pompeii is a dramatic story. It is the deeper, quieter story of why some of the most densely populated agricultural regions on Earth happen to sit in the shadow of active or recently active volcanoes. People go where the soil is good. The soil is good where the volcanoes have been working. This is a reasonable arrangement, as long as you maintain a certain flexibility about long-term planning. The three volcanoes of this chapter, one that appeared in a cornfield, one that is currently adding square kilometers to an island in the Pacific, one that generates its own thunderstorms during eruptions, represent only a narrow slice of volcanic behavior. There are fissure eruptions that produce vast lava fields spreading horizontally rather than building cones. There are calderas, enormous collapsed craters left when a volcano empties its magma chamber and the summit collapses inward. Yellowstone's caldera is large enough that people drive across it without necessarily realizing they are inside a volcanic structure. There are underwater volcanoes building seamounts and mid-ocean ridges across the floors of every ocean basin. There are volcanic systems so large that they are classified as supervolcanoes, with eruption histories so far beyond human scale that they are more usefully discussed in terms of mass extinction events than in terms of individual eruptions. The range of volcanic expression on this planet is, like most things on this planet, considerably wider and stranger than the standard frame of reference suggests. What connects all of it is the same force. The Earth's interior is still hot enough after 4.5 billion years to melt rock and move it toward the surface. The planet has not cooled down, it is not finished. It is still, in the most basic physical sense, burning through its own history, and the volcanoes are where that burning occasionally makes itself visible. From the fire that builds, it is a natural step to consider the life that follows. Because once volcanic rock has weathered to soil, once the mineral content is in place and the water is arriving, what grows can be extraordinary. And in certain places on Earth, what has grown has been growing for so long and has become so complex that the result is not merely a forest but a complete autonomous system. A world operating by its own internal logic, with its own climate, its own nutrient cycles, its own evolutionary relationships so intricate that scientists studying them are still, after decades of work, finding things that have not been catalogued yet. The laurel forests of Madeira are among the oldest intact forest ecosystems in Europe, and they are old in a way that requires some historical context to appreciate. During the warm period that preceded the last ice age, roughly 30 million years ago, the European continent was substantially warmer and more humid than it is today. Forests of laurel and related subtropical tree species, genera like Laurus, Ocotea, Persea, and Apollonius, covered a significant portion of what is now southern Europe and the Mediterranean basin. When the climate cooled and dried as the ice ages began approximately 2.5 million years ago, most of these forests retreated and eventually disappeared from the mainland, replaced by the more cold-resistant deciduous and Mediterranean scrub ecosystems we know today. The laurel forests of the Macaronesian Islands, Madeira, the Canaries, the Azores, survived because the island's oceanic climate buffered them from the worst of the temperature shifts. They are, in the most literal biological sense, survivors of a Europe that no longer exists. Walking into the Laurisilva forest on Madeira, which covers roughly a third of the island and has been a UNESCO World Heritage Site since 1999, is walking into a version of the Miocene landscape that most of the European continent has long forgotten. The first quality of the Laurisilva that strikes a visitor is the moss. Everything is covered in it, not a polite coating, but a deep, thick, comprehensive upholstery that covers trunks, branches, boulders, fallen logs, and the ground with equal thoroughness. The mosses are not one species but dozens, layered over each other in shades ranging from bright yellow-green to deep emerald to almost grey-blue, creating a depth of texture that makes the forest look permanently damp, which it is. Madeira sits in the path of trade winds that carry moist Atlantic air across the island, and the higher elevations, where the Laurisilva is most intact, are frequently enveloped in cloud. The water condenses on the tree canopy and drips continuously to the ground, a process called fog drip, or horizontal precipitation, which contributes water to the forest's hydrology, above and beyond ordinary rainfall. The trees, in effect, extract moisture from clouds passing through them. They are running their own water collection operation, and they have been doing it successfully for millions of years, which puts most human water management systems in a somewhat unflattering comparative light. The tree species themselves are ancient. The till tree, Ocotea futens, is one of the dominant canopy species and can live for several centuries, reaching trunks of extraordinary girth. The laurel of Madeira, Laurus novacanariensis, is the direct ancestor of the bay laurel used in cooking since ancient Roman times. The Madeira mahogany, Persea indica, produces a dense, aromatic wood that was heavily exploited during the centuries of Portuguese colonization of the island and is now protected. Walking through the older sections of the Laurisilva, the trunks of these trees are vast by European standards, not in the category of the giant sequoias we will encounter later, but substantial enough that a single tree can take several people joining hands to encircle. The canopy closes overhead, and the light changes immediately on entering, becoming green-filtered and diffuse in the way that only old-growth canopy can produce, shutting out the direct sun and replacing it with something slower and more interior. The biodiversity of the Laurisilva is extraordinary relative to the island's size. Madeira is roughly 740 square kilometres, smaller than Greater London, and yet its native forest harbours species of birds, insects, and invertebrates found nowhere else on Earth. The laurel pigeon, Columbatrocas, is a large, striking pigeon found only in Madeira, its entire wild population dependent on the Laurisilva for food and nesting. The Zeno's petrel, Pterodroma madeira, one of the rarest seabirds in the world, nests in cliff sites accessible only through the forest. Hundreds of invertebrate species, including beetles and land snails, are endemic to the island, their evolutionary lineages tracing back to the same Miocene ancestors as the trees they inhabit. When a forest has been stable enough for long enough, the organisms living in it begin to evolve along with it, producing species specifically adapted to that particular forest's microhabitat. The Laurisilva is not just old, it has been old long enough for its inhabitants to become uniquely, irreversibly its own. The levadas of Madeira, a system of irrigation channels originally built during the 15th and 16th centuries to carry water from the wet north of the island to the drier south, provide much of the forest access that visitors use today. The channels run along the contour lines of the mountains, maintaining their gradient with remarkable precision, and the paths alongside them have been used for centuries by maintenance workers keeping the channels clear. Hiking the levada paths through the Laurisilva gives a walking view of the forest's interior at roughly constant altitude, moving through the canopy at close range for hours. It is, practically speaking, one of the more effective ways to spend a day on an island that is very good at providing ways to spend a day. The levada system covers roughly 2,200 kilometers in total, which is more than sufficient for the purposes of forest exploration even if you are an extremely dedicated walker. If the Laurisilva represents ancient forest at a human scale, walkable, comprehensible, intimate in its mossy abundance, then the Amazon represents ancient forest at a scale that defeats human comprehension almost entirely. The Amazon basin covers roughly 5.5 million square kilometers, spanning 9 countries and encompassing the largest tropical rainforest on Earth by a substantial margin. It contains an estimated 400 billion individual trees from roughly 16,000 species, which is a figure that lands with a solid thud and then fails to produce any useful mental image because the human brain is not equipped to visualize 400 billion of anything. The basin's rivers carry approximately 20% of all the fresh water that enters the world's oceans. The forest itself generates roughly 20% of the Earth's terrestrial oxygen through photosynthesis, which is the source of the planet's lungs characterization, though ecologists will note with some justification that the Amazon also consumes roughly the same amount of oxygen through respiration and decomposition. The net oxygen contribution to the atmosphere is more complicated than the headline suggests, even as the forest's role in global carbon cycling remains genuinely critical. The Amazon's age is difficult to state simply. The tropical climate of South America has supported complex forest ecosystems for tens of millions of years, but the specific configuration of the current Amazon, its current rivers, its current species composition, its current drainage patterns, is considerably younger than that, shaped by the geological history of the Andes, which rose dramatically over the last 10 to 15 million years and fundamentally altered the drainage of the entire continent. Before the Andes reached their current height, the Amazon River system drained westward into what is now the Pacific. The current eastward flow into the Atlantic developed relatively recently in geological terms. The species that currently inhabit the Amazon have been evolving and diversifying for millions of years, but the forest as it exists today is both ancient and dynamic, not a static relic but a continuously evolving system that has survived ice age contractions and expansions, shifts in sea level, and changes in climate patterns over geological time. What makes the Amazon's biodiversity staggering is not just the total number of species, which is variously estimated but universally described as extraordinary, but the density of that diversity and the specificity of its distribution. A single hectare of Amazon rainforest can contain 200 or more species of tree, more than in the entire temperate forest biome of North America. A single tree can host hundreds of species of insect, many of them found only on that tree species in that particular region of the forest. A single river bend can contain fish species found nowhere else on Earth, isolated by the particular chemistry or current pattern of that stretch of water. The Amazon is not just diverse, it is diverse in a fine-grained, hyperlocal way that means each part of the forest is, to some degree, its own ecosystem with its own suite of specialists. This localization of species has made the Amazon particularly vulnerable to fragmentation. When a section of forest is cleared, it is not merely a reduction in total forest area. It is the elimination of particular local ecologies that may not exist anywhere else. The species that depend on those microhabitats cannot simply relocate to the nearest intact forest fragment. In many cases, those species are already at the edge of their range, and the fragment they depended on was the full extent of their world. Conservation biology in the Amazon is, in part, the science of understanding which fragments matter most, which species have the least tolerance for habitat reduction, and which corridors between fragments are critical for allowing movement and genetic exchange between populations. It is complex, expensive work, and the pace of deforestation in the Amazon over the last several decades has given researchers considerably more material to study than any of them would have preferred. The Amazon River system is not one river, but a network of thousands, ranging from the main channel, which in places is so wide that the opposite bank is below the horizon, to tiny forest streams running over black water stained by tannins from decomposing leaves. The blackwater rivers of the Amazon, called igapos, are notably acidic and low in nutrients, and the fish species that have evolved to inhabit them are specifically adapted to those unusual conditions. The famous ornamental fish trade, the neon tetras, discus, and cardinal tetras kept in aquariums around the world, draws largely on species native to these black water tributaries, their vivid colours evolved in the dark. Tannic water of Amazonian streams rather than in the bright clean tanks where they now spend most of their lives. This transition from Rio Negro tributary to suburban fish tank is, if you think about it, a fairly significant change of scenery. The forest's capacity to generate its own weather is one of its most remarkable and underappreciated features. The Amazon produces enormous quantities of water vapour through transpiration, the process by which plants release water through their leaves. This vapour rises, condenses into clouds, and falls again as rain, in a recycling loop that can be sustained across vast distances. Studies of water isotopes in Amazon rainfall have shown that a significant proportion of the rain falling deep in the interior of the basin has already cycled through the forest multiple times, evaporated from the leaves of trees, rained, taken up by roots, transpired again, condensed again. The forest is not just dependent on rainfall, it is partly manufacturing its own rainfall. This feedback loop is one of the reasons that large-scale deforestation can produce regional rainfall reduction, even in areas some distance from the deforested zone. The moisture recycling system breaks down when the trees that drive it are removed. The Amazon's relationship with fire is also worth understanding, because it is not the simple story that gets repeated in annual news cycles. The forest is not naturally fire-prone. Old-growth tropical rainforest is wet enough and structurally complex enough that fire moves through it only with great difficulty. The fires that have become a periodic feature of Amazon news coverage are overwhelmingly fires set intentionally in recently cleared or degraded forest, where the moisture has been reduced and the fuel load from cleared vegetation is high. Intact primary forest does not burn easily. The burning of the Amazon is a human management decision expressed at continental scale, which makes it categorically different from, say, the natural fire regimes of savannas or fire-adapted boreal forests, where periodic burning is part of the ecosystem's normal function. The Amazon did not evolve with fire. It evolved around the assumption that fire would not come. This is relevant because it means the forest has very limited regenerative capacity after burning, in comparison to ecosystems that have historically coexisted with periodic fire. The indigenous communities of the Amazon, roughly 400 distinct groups speaking more than 200 languages, have accumulated knowledge of the forest biology, medicine, and ecology over periods of time that make any university-based research program look rather recent by comparison. Ethnobotanical research over the last several decades has documented thousands of plant species with medicinal or practical applications that indigenous communities have been using for generations, and the pharmacological investigation of those plants has produced or contributed to numerous modern medicines. The relationship between indigenous knowledge and formal scientific knowledge in Amazonian research is complex and not without its historical controversies, but the basic principle that people who have lived in a forest for thousands of years know things about it that people who arrived recently are still figuring out is increasingly well recognized in the scientific community, if not always well implemented in practice. The Amazon and the Laura Silva, separated by an ocean, share a quality that distinguishes ancient forest from younger ecosystems: depth. Not just ecological depth, though that is certainly present in both. A different kind of depth, the depth that comes from time and from the accumulation of relationships between species, between organisms and their environment, between the living forest and the geology and climate that shaped it. A plantation forest and a primary rainforest can contain the same number of trees per hectare, and yet have almost nothing biologically in common, because the plantation has none of those accumulated relationships. It is a collection of trees. The primary forest is a civilization of trees, with all the complexity and internal logic that word implies. This is what gets lost, in the most irreversible sense, when ancient forest is cleared. Not just carbon storage, not just species counts, not just watershed protection, though all of those are real and significant. What gets lost is the time, millennia of coevolution, of ecological specialization, of microhabitat development. The moss on a Laura Silva tree trunk is not just moss. It is a specific community of species that has been developing in that specific microhabitat for longer than most human institutions have existed. Clear the tree and the moss goes with it, and what replaces it, if anything replaces it at all, will take an amount of time to develop that is not useful to think about in human terms. The planet builds forests the same way it builds caves and salt flats, slowly, incrementally, over periods of time that dwarf human civilization by orders of magnitude. The volcano erupts, and the basalt weathers and the soil forms, and the pioneer species colonize, and the forest builds itself up layer by layer over millions of years. It is, as these things tend to be, a process of extraordinary patience producing extraordinary results. And unlike a cave, which stays where it was formed, a forest is always in the process of becoming. It is never finished. It is never a finished product. It is always, in some sense, still happening. Which is, it turns out, true of most extraordinary things on this planet. There is a persistent and somewhat unfair assumption that deserts are boring. The word itself conjures a mental image that is, almost universally, incorrect. An expanse of golden dunes, a bleached sky, a camel looking skeptical in the middle distance. This image applies to perhaps 15% of the world's desert surface. The rest is rock, gravel, salt, clay, frozen tundra, and in certain spectacular cases, formations of stone so strange and so precisely sculpted that the people who first photographed them had a reasonable amount of trouble convincing audiences that the images were real and had not been assembled in a studio. Deserts are, at their core, places where water is absent or scarce enough that its usual geological role, the patient dissolving and transporting and depositing it does everywhere else, is replaced by a different set of forces: wind, temperature extremes, chemical weathering, and above all time operating without interruption on exposed rock. The absence of water means the absence of vegetation cover. The absence of vegetation cover means the absence of soil building. The absence of soil building means the rock is naked, exposed, available. In a forest, the geological processes happening beneath the surface are hidden under meters of organic material, root systems, and living organisms. In a desert, the geology is right there, visible, unmediated. This is why geologists find deserts so useful, and why photographers find them so overwhelming. The landscape has no secrets, no soft edges, no comfortable middle ground. Everything is what it is, with no biological apology for being that way. The White Desert of Egypt, known in Arabic as the Sahara El Beida, occupies a section of the Farafra Depression in the Western Desert, roughly 500 kilometers southwest of Cairo. The Egyptian Western Desert is already one of the more extreme environments on Earth in terms of basic hospitality. Temperatures in summer regularly exceed 50 degrees Celsius during the day and drop to near freezing at night. Precipitation is essentially theoretical rather than practical, and the nearest meaningful source of water is underground. The Farafra Oasis, the closest inhabited area, survives on ancient aquifer water that has been accumulating underground for millennia, from a period when the Sahara's climate was dramatically wetter than it is today. That wetter period, called the African Humid Period or the Green Sahara, ended roughly 5,000 to 6,000 years ago, and the speed of the climate transition, relatively fast by geological standards, though of course glacially slow by human ones, caught the inhabitants of the region in the process of adapting to a landscape that was changing faster than their culture could comfortably manage. But before the desiccation, before the sand dunes and the extreme aridity, the area that is now the White Desert was covered by a shallow sea. The brilliant white formations that give the desert its name are chalk, calcium carbonate deposited by the shells and skeletons of marine organisms across millions of years of seafloor accumulation, compressed and lithified, then slowly lifted above sea level by tectonic processes, and finally left exposed as the surrounding softer sediments eroded away. The chalk of the White Desert is among the purest and most visibly white limestone formations anywhere in the region, and its colour in direct sunlight is genuinely dramatic, a landscape of dazzling white against the ochre and tan of the surrounding desert floor. What makes the White Desert more than simply a white landscape is what the wind has done with the chalk over the centuries. The desert experiences strong winds, particularly the Khamsin, the hot desert wind that blows across Egypt from the south, carrying fine sand particles at speed. These sand particles act as an abrasive, eroding the chalk formations from the base upward, creating a phenomenon called differential erosion. The lower sections of the chalk outcroppings are worn more aggressively than the upper sections, because wind-driven sand travels primarily along the surface rather than at height. The result is a collection of shapes that look less like geological formations and more like the props department of a moderately ambitious science fiction production. Massive mushroom shapes with thin necks and broad caps, columns tapering toward the base and spreading overhead, arched formations, isolated pillars, and in some areas, shapes that bear an uncanny resemblance to animals, chickens, rabbits, and various other things that visitors tend to report having seen in the rock, because the human brain is constitutionally incapable of not finding faces and recognizable shapes in random objects. The White Desert obliges this tendency more generously than almost any other landscape on Earth. The chalk formations fluoresce slightly in certain light conditions. At sunrise and sunset, when the low angle of the sun turns the surrounding desert floor warm gold and rust, the white chalk formations catch the light and glow faintly, a pale luminescence against the darker sand. At full moon, the formations are visible from a considerable distance, catching the lunar light and standing out against the dark desert floor with a quality that multiple generations of travellers have described as ghostly, which is either a testament to the emotional impact of the landscape or evidence that people who travel to remote Egyptian deserts tend toward the literary in their self-expression. Probably both. Camping in the White Desert, which is an increasingly organised activity, with licensed guides and designated sites, which the formations seem entirely indifferent to, means waking to the chalk formations in the dark hours before dawn, when the stars over the Egyptian desert reach a density and clarity that most urban dwellers have never experienced, and watching the light change across the chalk as the sun comes up. The temperature differential between night and desert dawn is considerable, and the silence in the absence of wind is the kind of silence that feels physical, like a material property of the air rather than simply the absence of sound. The White Desert has a quality of complete removal from ordinary experience that visitors consistently describe as disorienting in a positive way, which is perhaps the most honest recommendation any landscape can receive. The geological history embedded in the chalk formations is, to those who read it, a deep-time narrative of considerable drama. The marine organisms whose shells built the chalk lived in a warm, shallow sea that covered the northern Sahara around 80 to 90 million years ago, during the Cretaceous period, the era of the large theropod dinosaurs, of which the inhabitants of this particular sea were entirely unaware. As they were marine organisms and the dinosaurs were inconveniently terrestrial, the sea retreated, the sediments consolidated, the land rose, the climate changed, the Sahara formed, the wind arrived, and eventually you have a landscape of white mushroom-shaped sculptures in the middle of one of the world's largest hot deserts. It is a reasonably long journey from seafloor to tourist destination, but the planet operates on schedules that accommodate this kind of extended itinerary. The Bisti Badlands of New Mexico operate on a similar principle: exposed geology, differential erosion, unprotected rock, but with an entirely different cast of minerals and a correspondingly different visual result. Bisti, pronounced roughly Bisti, is a Navajo word meaning large area of adobe hills, which is accurate enough as descriptions go, though considerably less evocative than the landscape deserves. The Bisti/Dinazin Wilderness, as it is formally designated, covers about 45 square kilometers in the San Juan Basin in northwestern New Mexico, in a region that was, 65 to 75 million years ago, a vast coastal swampland at the edge of the Western Interior Seaway, the inland sea that bisected North America during the Cretaceous, stretching from what is now the Arctic to the Gulf of Mexico. The sedimentary layers at Bisti were laid down in that ancient coastal environment: river channels, swamp deposits, floodplain clays, coastal marine sediments, all stacked in alternating layers of sandstone, shale, siltstone and coal seams. Each layer has a different hardness, a different resistance to weathering, a different colour determined by its mineral composition. The coal seams, when exposed at the surface and then eroded away, leave behind zones of clinker, baked and hardened sediment from the heat of ancient coal fires, some of which burned for centuries when the coal seams were exposed and ignited by lightning or wildfire. Clinker weathers differently from surrounding sediment, contributing yet another texture and colour to an already complex layering. The sandstone contains iron oxides in various concentrations, producing reds, yellows, and oranges. The clays are grey and lavender and white. The coal is black. The result, when wind and water erosion carve through all these layers at different rates, is a landscape of such chromatic and morphological complexity that it looks, to the modern eye, almost computationally generated. The formations called hoodoos, columns of softer rock capped by harder rock that protects them from erosion, while the surrounding material is stripped away, are a defining feature of Bisti. The hoodoos here range in scale from 0.5 metre to several metres tall, and they occupy the landscape in clusters that give the impression of a frozen population. Figures standing at various angles capped with dark sandstone or coal remnants, their bases of eroded clay giving them an unstable teetering quality that is real in the sense that they are actively eroding and will not be standing in their current form forever. But that is not an immediate practical concern. The hoodoo forming process requires a caprock harder than the substrate below, and Bisti obliges this requirement with its mix of coal fragments and harder sandstone nodules sitting on softer clay and shale. The results, photographed against the blue New Mexico sky or the amber light of late afternoon, produce images that have been used in science fiction media to represent alien planetary surfaces, and not without justification. Bisti also contains what are perhaps its most distinctive features, the so-called alien eggs, or dinosaur eggs, which are large, round, rust-coloured nodules of harder ironstone that weather out of the surrounding clay as the softer material erodes. They sit on the clay surface individually or in clusters, some of them split open to reveal the concentric banding of their internal structure, which does genuinely look like the contents of some enormous reptilian egg, assuming the reptile in question had a rather mineral-heavy diet. The nodules are not actually eggs. They are concretions, formed when mineral-rich groundwater precipitated iron oxides around a nucleus in the ancient sediment. But the name has stuck, and the formations have become among the most photographed features of the wilderness area. The fact that the Cretaceous swampland environment that these sediments represent was actually home to dinosaurs, including hadrosaurs, ceratopsians, and large carnivorous theropods, makes the egg comparison feel less like a stretch and more like a reasonable geological joke. Getting to Bisti requires navigating roads that are, in the polite terminology of New Mexico land management materials, improved dirt roads, which is a description that covers a wide range of experiences depending on recent weather conditions. The wilderness designation means no established trails, no signs, no facilities, and no particular assistance in navigation once you leave the parking area. The Badlands terrain, deeply dissected with gullies and clay hills that look identical from every direction, is genuinely disorienting, and people regularly get turned around in ways that would not happen in a more conventionally organized landscape. Compasses function normally, but the topography provides no useful landmarks because the topography is, essentially, all landmark and none of it distinguished from any other part of itself. This is, depending on your personality, either a serious logistical problem or a significant part of the appeal. The Bozhira Tract in the Mangistau region of western Kazakhstan is a location that most people outside the Central Asian geological and adventure travel communities have probably not heard of, which is entirely unreasonable given what it looks like. Mangistau sits on the northeastern shore of the Caspian Sea, in a region that is, by most standard measures of landscape quality, not promising. Flat, dry steppe, the kind of vast open terrain that you can drive through for hours without seeing anything that demands your particular attention. And then, somewhere in the interior of the plateau, the ground simply stops, and you're standing at the edge of a depression that extends 10 to 15 kilometers across and several hundred meters down, its floor white and cracked, its walls forming vertical and near-vertical cliffs of brilliant white and cream limestone. The Bozhira Hollow is a result of tectonic downdropping combined with subsequent erosion. The plateau surface cracked along fault lines, sections subsided, and erosion carved the exposed limestone cliffs that now define the site. The limestone here is of marine origin, similar in this respect to the chalk of the Egyptian White Desert, deposited in the ancient Tethys Sea that once covered much of what is now Central Asia and the Middle East. The Tethys Sea began closing roughly 65 million years ago, as the Indian subcontinent collided with Asia, and the broader tectonic reorganization of the region progressed, and the uplift that created the modern landscape of Central Asia produced the plateau from which Bozhira's cliffs descend. The formations within the depression include the features that have generated the site's growing reputation in the travel photography community: isolated towers of white limestone rising from the flat floor, narrow fins of rock extending from the cliff face like the prows of enormous ships, and in one memorable case, a stacked layering of light and dark bands in a natural pillar that local people have taken to calling tiramisu because the alternating cream and chocolate brown layers of rock bear, under certain lighting conditions, a reasonable visual resemblance to the dessert. This is an entirely appropriate name, delivered with the kind of deadpan observational humour that is, in the author's experience, a hallmark of Central Asian geographic nomenclature. The rock formation is ancient Tethys Sea sediment. It looks like dessert. These are both true simultaneously, and the fact that someone noticed the resemblance and named the rock accordingly says something pleasant about the human tendency to find familiar things in unfamiliar landscapes. Mangistau as a region contains several other significant landscape features within driving distance of each other, making it one of the more concentrated areas of geological spectacle in Central Asia. The Valley of Bulls, or Torish, is a field scattered with hundreds of perfectly spherical concretions of various sizes, the same formation process as the ironstone nodules of Bisti, but here producing spheres up to 4 meters in diameter. Sitting on the surface of a clay plain like marbles left by an absent-minded titan. The Aral Sea's eastern shore, once a productive fishing area, and now a vast stretch of exposed former seabed, lies within the region, a different kind of desert entirely, one created within living memory by the diversion of the rivers that fed it in the Soviet era, its abandoned fishing boats sitting rusting in the middle of what is now dry land. The combination of ancient geological spectacle and recent human-caused catastrophe in a single regional landscape gives Mangistau a complexity that purely scenic areas cannot match. The desert landscapes of this chapter are united by a quality that is worth naming explicitly. They are all places where the normal visual conventions of the natural world have been suspended. In a forest, organic shapes dominate. Curved, soft-edged, irregular in the way that living things are irregular. In a grassland or savanna, horizontal continuity defines the view. In a river valley, the logic of water moving downhill provides an organizing principle for everything you see. But in the White Desert, in Bisti, in Bozjira, the visual logic is something else entirely. Architectural, abstract, in some cases almost computational. The forms are too specific to be random and too strange to be familiar, and the brain, which spends most of its time successfully categorizing what it sees into known things, finds itself operating without adequate reference points. This is unsettling in a way that is ultimately pleasurable, the kind of unsettling that comes from encountering something genuinely new, as opposed to the kind that comes from encountering something dangerous. The specific quality of light in desert environments amplifies this effect. With no vegetation to scatter and absorb light, no cloud cover to diffuse it, no atmospheric humidity to soften it, desert light at mid-latitude locations is extraordinarily direct and hard-edged. Shadows are sharp. Colours are saturated. Textures on rock surfaces are rendered with a clarity that indoor lighting cannot replicate. Photographers who work in desert environments consistently report that the challenge is not finding visually interesting material that is everywhere, but managing the exposure extremes between bright rock faces and deep shadow, which can span a range that exceeds the dynamic capacity of most camera sensors. The White Desert at noon is, in this sense, one of the more technically demanding photographic environments on Earth, despite being one of the most visually spectacular. Nature, as ever, is not particularly concerned with convenience. The wind's role as sculptor in all three of these deserts deserves a moment of direct consideration, because it operates so differently from water that the results it produces feel governed by different aesthetic principles. Water flows downhill and follows the path of least resistance, carving channels and valleys in patterns that are always gravitationally organized. You can look at a water-carved landscape and trace the logic, understand the drainage, see how one feature leads to another. Wind does not observe gravity in the same way. Wind changes direction. Wind carries different particle sizes that abrade at different heights. Wind accelerates around obstacles and creates turbulence that erodes in unexpected directions. Wind-carved landscapes have a quality of apparent arbitrariness that water-carved landscapes do not, even when the underlying geology is the same. Two chalk outcroppings in the White Desert, standing side by side, can end up looking completely different from each other simply because one was exposed to slightly different wind patterns over the past 10,000 years. The wind does not follow a plan, and neither do the forms it creates. This quality of planless production is part of what makes wind-carved desert landscapes feel specifically alien, in the sense of unfamiliar rather than extraterrestrial. Though photographs of Bisti have in fact been used to represent Mars in various media productions, which speaks to the degree of visual overlap between our most extreme desert landscapes and the surface of the next planet outward from the Sun. Mars is, in geological terms, a very old desert planet with substantial wind erosion history and no liquid surface water to speak of. The closest planetary analogue to Earth's desert badlands, which is either reassuring or mildly ominous depending on one's perspective on planetary futures. There is also the question of what lives in these environments, which is never as simple as nothing. The White Desert supports populations of white desert foxes, whose pale colouring is an adaptation to the chalk landscape so precise that they are almost invisible against the white rock. Desert monitor lizards inhabit the Egyptian Western Desert, ancient reptile lineages persisting in conditions that would be rapidly lethal to most vertebrates. The Bisti Badlands support nesting ravens, desert cottontails, and a range of invertebrates that have made their lives in the clay hills and hoodoos. Mangistau's steppe supports saiga antelope, the extraordinary hooked-nosed ungulates whose population numbers fluctuate dramatically with disease and environmental conditions, but which have been part of the Central Asian landscape for several million years. The deserts are not empty. They are selective. They accept residents who have the specific adaptations for the specific conditions, and they are not apologetic about the specificity of those requirements. The animals that succeed in extreme desert environments tend to share a suite of characteristics: reduced metabolic rates, highly efficient water retention, tolerance for temperature extremes, and in many cases behavioral adaptations that involve being active during the cooler parts of the day or night, and largely inactive during the peak heat hours. The white desert fox hunts mainly at dawn and dusk. Desert monitors are largely inactive during the hottest months, reducing their energy expenditure to a minimum during periods when prey is scarce. The saiga has a respiratory system with an enlarged nasal cavity that both filters dust and pre-cools inhaled air, a physiological engineering solution to desert breathing that is more effective than anything humans have designed for the same purpose. Desert life is, in the most literal sense, highly optimized. The selection pressure in extreme environments is as unforgiving as the environments themselves. The aesthetic dimension of desert landscapes connects, however obliquely, to the broader theme of this series: the planet producing things that look designed without being designed, that appear to follow rules without being rule-governed, that generate beauty as a side effect of processes that have no aesthetic ambitions whatsoever. The mushroom-shaped chalk of the White Desert was not shaped to look like a mushroom. The hoodoos of Bisti were not arranged for compositional effect. The tiramisu layers of Bujira were not ordered to resemble a dessert. Wind-moved sand, sand abraded rock, harder rock resisted longer than softer rock, and the differential left shapes that a human brain, confronted with them, finds extraordinary. The mechanism is straightforward. The result is startling. This gap between the simplicity of the process and the complexity of the outcome is, at this point in the series, becoming recognizable as one of the planet's defining patterns. It applies to the glowworm caves, to the marble chapels, to the mirror of Uyuni, to the ancient forests, to the volcanic lightning of Fuego. The Earth is not trying to be impressive. It is simply following its chemistry, its physics, its climate, its geology, with the complete indifference of a system that has no concept of an audience. The fact that there is an audience, that conscious beings evolved on this planet and then developed the capacity to find it beautiful, is, from the planet's perspective, entirely beside the point. From ours, it is the entire point, and there is still considerably more to see. Before moving forward, it is worth spending a moment on the broader category of Badlands as a landscape type, because the three sites covered so far, Egypt, New Mexico, Kazakhstan, represent different regional variants of the same underlying dynamic, and there are others across the planet that illustrate the principle just as vividly. The Drumheller Badlands in Alberta, Canada, are carved from sediments deposited during the same Cretaceous period as Bisti, and the erosion of the Horseshoe Canyon and Red Deer River Valley has exposed one of the most productive dinosaur fossil beds in North America. The Badlands there are red and grey and tan rather than the multicoloured palette of New Mexico, and the scale is different. Broader valleys, more open horizons, less of the labyrinthine quality that Bisti produces. But the logic is identical. Soft sedimentary rock, exposed by erosion, carved differentially by water and wind over thousands of years into forms that make the subsurface visible. The Danakil Depression in Ethiopia takes the concept of extreme desert landscape and adds a layer of geochemical spectacle that puts most other environments firmly in the category of manageable. Danakil sits in the Afar Triangle, a region where three tectonic plates are slowly pulling apart, the Arabian, Nubian and Somalian plates diverging at rates of a few centimetres per year, with the result that the land surface is actively subsiding. Parts of the Danakil Depression sit over 100 metres below sea level, making it one of the lowest points on Earth's surface, and the hydrothermal activity associated with the rifting has created a landscape of sulfur springs, salt formations, lava lakes, and acidic hot spring pools that operates at a level of visual drama beyond most comparisons. The Dalol hydrothermal field, located within the depression, contains hot spring pools of brilliant yellow, green, and orange, the colours produced by sulfur, iron oxide, and chloride minerals in the water. The temperatures at the spring vents exceed 90 degrees Celsius in places. The surrounding terrain is a crust of salt and mineral deposits in shades of white, yellow, brown, and rust, broken by vents and pools and the occasional collapsed salt pillar. Dalol holds the record for the highest average temperature of any inhabited location on Earth, though inhabited is doing significant work in that sentence, as the population consists primarily of Afar workers in the salt mining operations, rather than anything resembling a settled community in the conventional sense. The average annual temperature is around 34 degrees Celsius, which is the kind of statistic that makes you want to check the measurement methodology, and then, having confirmed it, check the flight options for somewhere considerably colder. The salt mining operations in the Danakil Depression have been conducted by the Afar people for centuries, using methods that have not changed dramatically in the intervening time. Workers cut slabs of salt from the lake floor with wooden and metal tools, load them onto camels, and transport them along ancient caravan routes to markets in the Ethiopian highlands. The salt slabs, called a mole, were historically used as currency in Ethiopia, a practical monetary system, since everyone needs salt and salt is difficult to counterfeit, which puts it ahead of several more sophisticated monetary innovations on both counts. The camel caravans that carry the salt out of Danakil travel the same routes that caravans have travelled for hundreds of years, through some of the most extreme terrain on Earth, at temperatures that are, frankly, not ideal for either the camels or the people. The Afar workers are, not to put too fine a point on it, considerably tougher than the average visitor. The Namib Desert in southern Africa represents yet another character in the desert cast. A coastal desert, one of the oldest in the world, shaped by the cold Benguela current that runs up the west coast of Africa and prevents moisture-laden air from reaching the interior. The Namib has been continuously arid for somewhere between 45 and 80 million years, making it one of the oldest deserts on Earth. Its most famous feature, the towering red sand dunes of Sossusvlei, are among the highest in the world, reaching over 350 metres. These dunes are extraordinarily old by sand dune standards, their red colour derived from iron oxide coating that has developed on the sand grains over millions of years of oxidation. Fresh sand is pale. Old Namib sand is rust red, the colour deepening with age, which provides geologists with a rough visual guide to dune age simply by looking at the colour gradient. The dead acacia trees of Deadvlei, a clay pan within the Sossusvlei area, have become one of the most iconic images of the Namib. The trees died somewhere between 500 and 900 years ago, when the dunes shifted and blocked the river channel that fed the pan. In the extreme aridity of the Namib, the dead trees did not rot. They simply desiccated and turned black, preserved in the dry air for centuries, standing in a white clay pan surrounded by rust-red dunes and a vivid blue sky. The visual composition is, to a photographer, almost unreasonably cooperative. The dead trees are black, the clay is white, the dunes are red, the sky is blue. The landscape has arranged itself in primary contrasts with a thoroughness that suggests a production designer with very strong opinions and an unlimited budget. This is, of course, the result of completely unrelated geological and biological processes operating independently, which somehow makes the result more satisfying rather than less. The life of the Namib, like the life of all extreme deserts, is built around unusual strategies. The fog-basking beetle, Stenocara gracileps, is perhaps the most famous organism of the Namib's coastal zone. In the morning, when cold Benguela fog rolls in from the ocean, the beetle climbs to the top of a dune and tilts its body at a precise angle to the fog, which condenses on bumps on its back. The water runs down channels between the bumps toward the beetle's mouth, providing it with drinking water in a desert where liquid water at the surface is essentially non-existent. This mechanism, collecting water from fog, has been studied extensively by engineers and materials scientists interested in applying it to water collection technology in arid regions, making the fog beetle's back surface one of the more practically influential natural structures in recent biomimicry research. The beetle has been doing this for considerably longer than engineers have been studying it, naturally, and without any patents. The oryx of the Namib has solved the desert heat problem through a different physiological strategy: selective brain cooling. During intense heat, the oryx allows its body temperature to rise considerably higher than most mammals can tolerate, up to 45 degrees Celsius, without dying. It does this by routing blood flow through a network of fine vessels in the nasal cavity called the carotid rete, where the blood is cooled slightly before reaching the brain. The brain stays cooler than the body, protected from the heat that would otherwise cause neurological damage at those temperatures. The oryx effectively runs its body as a radiator, and keeps its brain in an air-conditioned compartment within the same body, which is an engineering solution of considerable elegance, and one that required no conscious design, only millions of years of selective pressure in a very hot place. There is a pattern worth noting in how desert species have arrived at their various solutions to the same fundamental problems. The fog beetle collects water from air. The oryx cools its brain selectively. The white desert fox reflects heat with its pale coat. The desert monitor slows its metabolism to near standstill. The saiga pre-filters and pre-cools its air. None of these solutions were designed. All of them were arrived at through the same process: random variation, survival pressure, and the slow accumulation of functional traits over geological time. And yet each one is effective enough at its specific problem that engineers and materials scientists study them as models. This is what evolution produces when the selective environment is specific and the time available is sufficient. Solutions that work without any awareness that they are solutions. The Atacama Desert in northern Chile is, depending on the measurement criteria, either the driest non-polar desert on Earth or simply one of the driest places, and the argument about the ranking is the kind of thing that engages hydrologists and geographers with an enthusiasm that the general public perhaps does not fully share. What is not disputed is that parts of the Atacama receive no measurable rainfall for decades at a time. Some weather stations in the interior have recorded no precipitation for over 20 years. The Atacama sits in a double rain shadow, blocked from the Pacific by the coastal range and from the Amazon basin by the Andes, and lies adjacent to the cold Benguela-equivalent Humboldt Current, which suppresses precipitation in the same way the Benguela does in Namibia. The combination of these factors has produced an environment of extreme dryness that supports almost no visible biological life across large sections of its interior. The surface of the Atacama has been used by NASA and other space agencies to test rover and instrument designs for Mars exploration, for the straightforward reason that the Atacama is the closest analogue on Earth to the Martian surface in terms of dryness, UV radiation levels, and soil chemistry. Some areas of the Atacama's interior soil contain essentially no organic material, no bacteria, no fungi, no microbial life detectable with standard methods. This is extremely rare on Earth, where microbial life has colonized virtually every surface and environment on the planet. The Atacama's most extreme zones have defeated even the microbes, which is either impressive or faintly alarming. Recent research has found microbial life surviving within rocks in the Atacama, protected by the translucent mineral layers of the rock surface that allow enough light for photosynthesis while filtering the UV radiation that would be lethal at the surface. Life in the Atacama has gone underground, not in a cave system, but inside individual rocks, each one a tiny refuge in a landscape that has given up almost all other accommodations. The Atacama is also, somewhat improbably, excellent farmland at its fringes. The Atacamenian people have farmed the oasis valleys at the desert's edges for thousands of years, using the same ancient aquifer water that sustains Farafra in Egypt. The pre-Inca civilization of San Pedro de Atacama produced sophisticated irrigation systems, traded with Andean and lowland South American cultures, and developed a material culture of considerable complexity in the shadow of one of the harshest environments on Earth. The pattern established in the volcanic soil discussion of the previous chapter applies here in a different form. Human settlement near extreme environments is frequently explained by resources, water, minerals, agricultural potential, that make the extreme conditions a price worth paying rather than a reason to go somewhere more comfortable. The deserts of this chapter, across 3 continents and widely varying geological histories, share the quality of making the visitor feel genuinely small in a way that is different from other large natural environments. The Amazon makes you feel small through density and complexity. The forest closes around you, fills your field of view, presses in from all directions with biological abundance. A desert makes you feel small through openness and scale. The landscape recedes in every direction, the sky is enormous, the landmarks are widely spaced, and the geometry of the whole system is visible all at once in a way that forest never allows. Both sensations are valuable, both are honest. The forest reminds you that you are one organism among incomprehensible billions. The desert reminds you that the earth is very large and you are very specifically located within it. The wind, still moving, still carving. The desert's quality of openness, that sense of being able to see everything all at once, of the landscape withholding nothing, finds its precise opposite in the ocean. The ocean hides everything. It covers, operating at a pace and complexity that the deep sea cannot match. And within the global catalogue of reef systems, the waters around Raja Ampat in the Indonesian province of West Papua represent what many marine biologists will describe, with varying degrees of professional restraint, as the most biodiverse marine environment on Earth. Raja Ampat means four kings in Indonesian, a reference to the four main islands of the archipelago, Waigeo, Batanta, Salawati, and Misul, that sit off the northwest tip of the Bird's Head Peninsula of New Guinea. The surrounding waters lie within the Coral Triangle, a region bounded by Indonesia, Malaysia, the Philippines, Papua New Guinea, the Solomon Islands, and Timor-Leste, which contains the highest concentration of marine species anywhere in the ocean. The Coral Triangle itself is biodiverse by global standards. Raja Ampat is biodiverse by Coral Triangle standards, which makes it something like the superlative of a superlative, a situation that marine biologists find professionally exciting and that the Indonesian government has found economically useful in developing the area's conservation and tourism programs. The species counts for Raja Ampat read like someone got carried away with the catalogue function on a spreadsheet. Over 1,400 species of reef fish, more than 600 species of coral, roughly 75% of all coral species known to science, in an area covering roughly 46,000 square kilometres of sea, more than 700 species of mollusks, mantis shrimp whose eyes contain 16 types of photoreceptors compared to the 3 that human eyes contain, giving them a perception of colour that is so far beyond what we can conceive of that trying to imagine it is roughly as useful as trying to imagine a new primary colour. The mantis shrimp, for the record, is not particularly interested in sharing its perceptual experience with anyone, and is instead focused on using it to hunt prey with a striking appendage that accelerates at roughly the same force as a rifle bullet. The mantis shrimp is, by any reasonable assessment, one of the more over-engineered organisms in the ocean, but the ocean is not known for its commitment to minimalism. The coral reef itself, the physical structure that supports this extraordinary diversity, is built by coral polyps, tiny animals related to sea anemones that secrete calcium carbonate skeletons and live in colonies of millions of individuals. The skeletal structure accumulates over centuries and millennia to form the reef framework, which is then colonized by the full range of organisms that depend on it for shelter, food, and breeding habitat. A mature coral reef represents centuries of biological construction, a three-dimensional habitat of extraordinary structural complexity in which every crevice, every overhang, every sand patch, every current channel supports different communities of species. The reef is not just a collection of corals, it is a city, with neighbourhoods, with commuters, with specialists who never leave their specific microhabitat, and with opportunists who move through the whole system following the food. The coral of Raja Ampat includes species found nowhere else in the world, a result of the region's position at the intersection of the Indian and Pacific Oceans, which makes it both a meeting point for species from 2 ocean basins and a centre of origin for new species produced by the region's evolutionary isolation and productivity. The Wallace Line, the biogeographical boundary identified by the naturalist Alfred Russel Wallace in the 19th century, which separates the fauna of Asia from the fauna of Australasia, runs through this region, and the waters of Raja Ampat sit at and around this boundary, producing a mixing zone of extraordinary biological consequence. Wallace himself, who spent 8 years collecting specimens in the Malay archipelago in the 1850s and 1860s, and independently arrived at the theory of evolution by natural selection at roughly the same time as Charles Darwin, would have found the Raja Ampat marine environment both professionally fascinating and probably very wet, given the amount of time it would have required to study properly. Diving in Raja Ampat involves a visual experience that is difficult to prepare for even with extensive prior diving experience. The density of life on a healthy reef there is such that every surface is occupied. Corals layered over each other, fish moving in every direction, invertebrates in every crevice, the water column above the reef busy with schooling fish and the occasional large pelagic visitor. Manta rays are common in the region. Cruising along the reef walls with the particular unhurried efficiency of animals that have been doing the same thing for millions of years and are not concerned about the schedule. Whale sharks pass through seasonally. Wobbegong sharks, the carpet sharks that lie motionless on the reef floor and rely on camouflage so effective that divers occasionally kneel on them, a mutual surprise that neither party handles with particular grace, are resident. The pygmy seahorse, Hippocampus bargibanti, lives exclusively on specific fan corals, matching the coral's color and texture so precisely that it went undiscovered until 1969, when a scientist studying a fan coral in an aquarium noticed on close examination that part of the coral was a seahorse. The seahorse is roughly 2 centimeters long, which is relevant context for understanding how it managed to avoid scientific detection for as long as it did. The vulnerability of coral reef systems to temperature change has been one of the defining environmental stories of recent decades. Coral bleaching, the process by which corals expel the symbiotic algae that live in their tissues and provide them with nutrients through photosynthesis, leaving the white calcium carbonate skeleton visible, occurs when sea temperatures rise above the coral's thermal tolerance threshold, typically by just 1 or 2 degrees Celsius above the seasonal maximum. The algae, called zooxanthellae, are both the coral's primary food source and the source of the reef's characteristic colours. Without them, a coral is not immediately dead but is severely stressed, and if the bleaching persists for several weeks, the coral will starve. Mass bleaching events, affecting large areas of reef simultaneously during periods of elevated ocean temperature, have increased dramatically in frequency and severity over recent decades. The Great Barrier Reef experienced mass bleaching events in 2016, 2017, 2020, 2022, and 2024, a sequence that represents a rate of recurrence that gives the reef insufficient time to recover between events. Raja Ampat's position in waters that are somewhat cooler and more nutrient-rich than some other reef systems has provided partial protection, but the trajectory of ocean temperature change places all reef systems under increasing pressure regardless of their current health. Coral bleaching is, to put it plainly, what happens when the ocean gets a fever, and much like a fever in a human, the reef can recover if the temperature comes back down in time. The distinction between a reef that recovers and a reef that does not is, in a warming ocean, largely a question of how much time it gets between fevers. This is not a comfortable situation, and the people who study reef systems professionally are, as a general category, not the most relaxed group of scientists you will encounter. From the density and drama of Raja Ampat, the shift to Jellyfish Lake on the Palau island of Ale Malk is a shift in scale and pace to something much quieter and in its own way more extraordinary. Jellyfish Lake is a marine lake, a body of salt water connected to the ocean by tunnels through the rock, but isolated enough that it has developed its own distinct ecology, separated from the broader reef system. The lake covers roughly 5.5 hectares and reaches a depth of around 30 meters, and it has been isolated from the open ocean for roughly 12,000 years, since sea levels rose after the last glacial maximum and flooded the limestone islands of Palau. The golden jellyfish, Mastigias papua etpisoni, found in Jellyfish Lake, is a subspecies found nowhere else on Earth. Over the 12,000 years of the lake's isolation, the jellyfish population has evolved away from its ocean relatives in ways that reflect the specific conditions of the lake. Most notably, the lake's jellyfish have significantly reduced their stinging capacity. In the open ocean, mastigious jellyfish use their nematocysts, the stinging cells, to stun small prey. In Jellyfish Lake, there are no significant predators of the jellyfish, and prey is abundant as tiny zooplankton, so the energetic investment in maintaining a potent sting became unnecessary and was gradually reduced. The result is a jellyfish whose sting is so mild that most human visitors cannot feel it on skin, though people with particularly sensitive skin or who stay in the water for extended periods may notice a faint irritation. Swimming through millions of jellyfish and feeling essentially nothing is a sensory experience that is simultaneously peaceful and slightly surreal. The daily migration of the jellyfish through the lake is one of the more precise biological behaviours in any landlocked water body. The golden jellyfish hosts zooxanthellae, the same symbiotic algae that live in corals and provide nutrients through photosynthesis, which means the jellyfish needs sunlight to survive. Each morning, the jellyfish population congregates on the western side of the lake, where the first sunlight arrives. As the sun moves overhead, they migrate toward the centre. By afternoon, they are tracking the eastern shore, following the light. They do this as a mass, millions of jellyfish, all moving in the same direction, a translucent golden pulse through the turquoise water. In the evening, they descend to the thermocline, a boundary layer below which the water is anoxic and rich in hydrogen sulfide, where they apparently extract nutrients from the bacteria that thrive there, before returning to the surface the next morning to begin the cycle again. The lake is currently open to visitors under strict protocols, including limits on the use of sunscreen in the water, which contains chemicals harmful to the jellyfish, and the zooxanthellae they host. The open ocean, beyond the reefs and isolated lakes, is a different environment by every measure, vaster, more uniform at the surface, and stranger the deeper you go. The sperm whale's place in this chapter is not earned by its size, though a mature male sperm whale reaches up to 18 meters in length and can weigh 57 tons, making it the largest toothed predator in the history of life on Earth by a considerable margin. It is earned by what a group of marine researchers observed on a quiet afternoon in 2008 off the coast of the Azores, an archipelago in the North Atlantic roughly 1,500 kilometers west of Portugal. The research team was in the water conducting behavioral observations when they encountered a group of sperm whales that were not doing anything particularly dramatic. They were not feeding, not socializing, not traveling. They were hanging vertically in the water, heads pointed upward, completely motionless, their bodies arranged in a loose cluster just below the surface like a stand of tall, extremely large, sleeping at rest and in warm surface water. The spermaceti is liquid, and the whale is slightly positively buoyant. It naturally floats with the head up. This makes vertical sleeping the path of least resistance for an animal that is not actively swimming. The whale is, in a sense, using its own anatomy as a life jacket, floating vertically at the surface while its brain cycles through sleep stages that are now known to include periods resembling mammalian REM sleep. The discovery that sperm whales sleep in this manner took until 2008, not because sperm whales are rare. They have a global distribution and a population estimated at around 300,000, but because observing them doing it required the unusual combination of calm seas, a research team that happened to be in the water at the right moment, and the recognition that the behavior they were seeing was sleep rather than illness or some other state. The researchers on that first documented observation apparently approached the sleeping group quietly and paddled among the whales for a period before one of them woke, startled, and the group dove. The researchers described the experience of being in the water surrounded by sleeping sperm whales as something for which they had no adequate reference, which seems like a reasonable assessment. Sperm whales sleep for short periods, typically between 10 and 15 minutes per sleep session, spending on average around 7% of their time in sleep, which is considerably less than most land mammals, but consistent with other cetaceans. The reason for the brevity is practical. They are air breathers, and sleeping at depth would be fatal. The vertical posture at the surface allows them to breathe without fully waking, with the blowhole positioned just at or near the surface. The whale's blood has a higher concentration of hemoglobin than human blood. Its muscles have higher concentrations of myoglobin, and its diving reflex is far more pronounced than any human free divers, reducing heart rate to as few as 4 beats per minute during the deepest phases of the dive. The sperm whale is, physiologically, one of the most comprehensively adapted deep-sea hunters in the vertebrate world. The giant squid that the whales hunt are themselves among the least observed large animals on Earth. Architeuthis dux, the giant squid, reaches lengths of up to 13 meters including the tentacles, and its eyes are the largest of any living animal, up to 30 centimeters in diameter, a size that appears to have evolved specifically to detect the faint bioluminescent light of the deep ocean, where conventional eyesight would be useless. The ocean flickering and pulsing with the movements and communications of its inhabitants. The scale and variety of this bioluminescent activity is so extensive that oceanographers now consider it a fundamental feature of the deep-sea ecosystem, rather than an interesting curiosity of specific organisms. The functions of bioluminescence vary by organism and context. The anglerfish's lure, a bioluminescent appendage dangling above the fish's mouth, modified from its dorsal fin, is the most famous example of predatory bioluminescence, attracting prey in absolute darkness toward a waiting predator with extremely large teeth and an extremely small sense of fair play. Counter-illumination, in which animals produce light on their undersides to match the faint light from above and make themselves invisible to predators looking upward, is found in various squid and fish species and represents a sophisticated optical camouflage technique. Communication bioluminescence, used by various dinoflagellates and some squid species to signal potential mates or rivals, implies a level of social complexity in the deep that the environment's apparent bleakness would not suggest. And the simple, startling flash, produced by many organisms when disturbed, appears to serve as a disorienting defense, the underwater equivalent of a flashbang. The hydrothermal vents of the deep ocean floor are among the most important biological discovery of the 20th century, representing a complete revision of what was previously a fairly settled scientific assumption, that all food chains on Earth ultimately trace back to photosynthesis, to sunlight. The first hydrothermal vent ecosystem was discovered in 1977 by researchers aboard the deep-sea submersible Alvin in the Galapagos Rift Zone of the Pacific, at a depth of around 2,400 meters. The team but the vent tube worms represent perhaps the most structurally thorough version of it in the animal kingdom. The discovery of vent ecosystems opened a significant scientific discussion about the possibility of life in environments previously considered completely inhospitable, including the subsurface oceans of icy moons like Europa and Enceladus, where hydrothermal activity has been proposed to exist beneath kilometers of ice. If life on Earth can sustain itself through chemical energy in the complete absence of sunlight at extreme temperature and pressure, then the distribution of potential habitats for life in the solar system expands considerably. The deep-sea vent discovery did not just add a new ecosystem to the catalogue, it moved the boundaries of the possible. The ocean's trenches represent the deepest points on Earth's surface, and the Challenger, deep in the Mariana Trench, at nearly 11 kilometers below sea level, is the deepest known point of all. The pressure at this depth is over 1,000 times atmospheric pressure at sea level, enough to compress water measurably, which is not something water does under ordinary circumstances, as water is famously resistant to compression. The temperature is just above freezing, perpetually dark, and yet life exists here too. Amphipods, small crustaceans, have been collected from the Challenger Deep in significant numbers. Fish species have been filmed at depths exceeding 8 kilometers, far deeper than previously thought possible for vertebrates. Microbial communities exist in the sediment at the deepest depths, processing organic material that drifts down from the surface over years and decades. The Hadal Zone, as the regions below 6,000 meters are collectively called, has been explored by humans precisely 3 times in a crewed vessel, as of the early 2020s, by Jacques Picard and Don Walsh in the bathyscaphe Trieste in 1960, by the director James Cameron in a custom submersible in 2012, and by the explorer Victor Vescovo in the deep-sea vessel Limiting Factor in 2019. Vescovo's dive was also the deepest crewed descent ever recorded, reaching a depth of 10,928 meters, and during it he found, at the bottom of the deepest place on Earth, a plastic bag and candy wrappers. This detail has been cited frequently in discussions of ocean pollution, and it is cited here with the same mix of admiration for the achievement and dismay at the discovery that seems to be the appropriate response to it. The ocean remains, after all of this, largely unknown. The species we have identified represent a fraction of those that exist. The processes we have characterized represent a fraction of those that operate. The ecosystems we have mapped represent a fraction of those that cover the ocean floor. What we know about the ocean is, in the most honest assessment and introduction, a first pass through a catalogue whose full extent we cannot currently estimate. The coral reefs, the jellyfish lakes, the sleeping whales, the glowing deep-sea organisms, the chemosynthetic vent communities, all of these are windows into a world that is operating continuously, at depth, in darkness, in cold, in pressure, with no awareness of and no requirement for any human observer. The ocean does not need us to be extraordinary. It has been extraordinary for over 3 billion years, which is roughly when the first simple organisms appeared in the primordial seas, and it will continue to be extraordinary for a very long time after whatever current chapter of planetary history we happen to be in has concluded. This is not a comfortable thought exactly, but it is a grounding one. The planet's most complex ecosystem predates us by an enormous margin, and will outlast us by a similarly enormous one. We are, in the ocean's timeline, a brief and recent development. We have not even managed to find all the species yet. This seems like a reasonable place to maintain some humility. The question of what else is down there, not hypothetically but specifically, in terms of organisms and behaviours and ecological relationships, is one that oceanography keeps answering and then revising. In 2000, a research team in the South Pacific discovered a species of octopus that walks on 2 arms along the seafloor, using the other 6 arms to impersonate a rolling coconut, which it does while the predator it is fleeing watches from a distance, apparently confused. This is either proof of intelligence or evidence that the ocean produces creatures whose behavioural repertoire occasionally surprises even the creatures themselves. The mimic octopus, Thormoctopus mimicus, can impersonate a flatfish, a lionfish, and a banded sea snake by adjusting the shape and movement of its body and arms, and it apparently selects the mimicry target based on the type of predator threatening it, choosing sea snake impersonation specifically when being chased by damselfish, which are preyed upon by sea snakes. The octopus has learned, or evolved, a context-sensitive deception system. It picks its disguise based on the audience. There are comedy writers who aspire to that level of situational awareness and have not achieved it. The Coelacanth, Latimeria chalumnae, was thought to have been extinct for 65 million years, known only from fossils, listed in natural history texts alongside the dinosaurs and the ammonites as representatives of life forms that had been swept away by the mass extinction at the end of the Cretaceous. Then, in 1938, a museum curator named Marjorie Courtenay Latimer noticed an unusual fish in the catch of a local fishing trawler in South Africa, recognised it as something she had not seen before, and preserved it rather than discarding it. When the specimen reached the ichthyologist J.L.B. Smith, his response was, by his own later account, one of the more extreme reactions in the history of fish identification. The fish was a coelacanth, alive, having apparently not received the memo about its extinction. A second living specimen was not found until 1952 off the Comoro Islands, and a separate population was discovered off Sulawesi in Indonesia in 1998, which means that for 60 years science was aware of only one small group of these fish, and assumed they were restricted to the western Indian Ocean. The Indonesian population had been known to local fishers for generations. They occasionally caught them, found them too oily to eat palatably, and did not particularly publicise the matter. Science's discovery of a second population of living fossils was, in this sense, less a discovery than a formal introduction to something that had been going about its business quietly for decades. The ocean rewards this kind of extended attention. The more carefully you look and the deeper you go, the more it produces things that revise the assumptions you arrived with. This has been true since the first naturalists began dredging deep-sea samples in the 19th century and finding life where they expected to find nothing. It was true when the Trieste crew looked out their portholes at the bottom of the Challenger Deep in 1960 and saw a flatfish, an animal they genuinely did not expect to be there, moving along the sediment. It remains true today when remotely operated vehicles in the deep Pacific regularly return footage of organisms that have not been previously described. The ocean is the planet's largest archive of biological novelty, and it is still, in the most literal sense, open for reading. The ocean, for all its depth and mystery, operates largely in silence from a human perspective. Its most dramatic processes, the slow building of reef structures, the centuries-long accumulation of vent communities, the patient chemical cycling of its vast water column, happen at a pace and in a register that we can observe but not quite feel. Waterfalls are different. A waterfall is geology in a hurry. It is the moment when the long, slow accumulation of elevation meets gravity's complete indifference to that accumulation, and the result is not subtle. It is not patient. It is loud and physical, and present in a way that most natural processes are not, and the experience of standing near a significant waterfall involves the body as much as the eyes. The air pressure changes, the spray reaches your skin, the sound occupies the full range of audible frequency, and some that sit just below it, felt rather than heard. A waterfall is, among the Earth's geological features, about as close as you get to the planet doing something you can feel in your chest. Angel Falls in Venezuela is the starting point for this chapter, because it represents the waterfall concept taken to its extreme. At 979 metres, it is the tallest uninterrupted waterfall on Earth, not the tallest cascade, which would include step falls and series falls of various kinds, but the single longest continuous freefall of water from source to base. The water that goes over the edge of the Ollantaytambo tabletop mountain in the Canaima National Park of southeastern Venezuela drops nearly a kilometre before it reaches the bottom. For context, the Empire State Building is 443 metres to its roof. The water at Angel Falls falls more than twice the height of the Empire State Building in continuous free fall, and by the time it gets to the bottom, a significant portion of it has atomized into mist during the descent. On windy days, the mist drifts for kilometres. The Tepuis, the flat-topped tabletop mountains of the Guiana Highlands, of which Ollantaytambo is one of the largest, are among the most geologically ancient surfaces on Earth. They are remnants of a vast sandstone plateau that was once part of the supercontinent Gondwana, dating back roughly 1.7 billion years, and they have been slowly eroding for hundreds of millions of years as the softer rock surrounding them has worn away, leaving the harder sandstone cap standing above the surrounding lowland forest. The Tepui are, in this sense, islands of ancient rock surrounded by an ocean of time, their flat summits hosting ecosystems that have evolved in isolation for millions of years, with species of plants and insects found nowhere else on Earth, and their vertical walls plunging hundreds of meters to the jungle below. Angel Falls itself was not unknown to the indigenous Pemon people who lived in the region for centuries before any outside documentation of it, which is worth stating plainly because the history of European and American discovery of natural landmarks in indigenous territories has a somewhat complicated relationship with the concept of discovery. The falls were known to the Pemon as Kerepakupai Meru, meaning waterfall of the deepest place, which is a considerably more accurate and poetic name than what they were eventually assigned in international usage. The name Angel Falls comes from Jimmy Angel, an American bush pilot who flew over the falls in 1933 while searching for a gold-bearing ore river, an occupation that was legal at the time, and also spectacularly unsuccessful in his particular case. Though he did correctly report the extraordinary waterfall he had flown over, Angel later landed his monoplane on the summit of Ollantaytambo in 1937 in an attempt to find gold deposits, got the plane stuck in the boggy ground on the summit, and had to hike 11 days back down through the jungle with his wife and 2 companions. The plane remained on the summit of Ollantaytambo for 33 years before it was eventually helicoptered out and is now displayed at Ciudad Bolivar Airport. Angel's name on the waterfall is essentially the consolation prize for a gold hunting expedition that did not go as planned, which is a less romantic origin story than most visitors assume. The approach to Angel Falls involves a combination of small propeller aircraft and motorized dugout canoe through the river systems of Kanama National Park, a journey that takes the better part of 2 days and delivers visitors to a camp at the base of the Tepui, from which the falls are visible on clear days as a thin white thread descending the cliff face. The falls are not always visible. The region receives over 2,000 millimeters of rain per year, and cloud cover on the Tepui is frequent, sometimes obscuring the entire upper falls for days at a time. This is the kind of variability that travel planners in the region have to manage diplomatically, since the difference between a guest who arrives in clear weather and sees the full 979 meters and a guest who arrives in cloud and sees nothing is approximately the difference between a 5-star review and a very measured one. The falls naturally are unaware of and unbothered by TripAdvisor. The volume of water going over Angel Falls varies dramatically with the rainy and dry seasons. During the dry season, from December to April, the flow can reduce to a relatively thin stream, with much of the water atomizing before reaching the base. During the peak of the rainy season, from June to September, the falls run full and the spray at the base reaches the surrounding jungle several hundred meters away. The full, heavy-flow version of Angel Falls produces a visual effect that genuinely defies casual description. The white column of water, a kilometer tall, disappearing into mist before reaching the ground, the surrounding Tepui walls red-orange with water stains and black with organic deposits. The jungle below dark green and completely indifferent to the spectacle above it. It is, on its peak days, the kind of sight that resets the viewer's internal scale for what dramatic means. The Iguazu Falls on the border between Argentina and Brazil represent an entirely different model of waterfall, not height, but breadth and sheer hydrological mass. Where Angel Falls is a single, extraordinary vertical plunge, Iguazu is a system of 275 individual falls spread across a horseshoe of cliff edge nearly 3 kilometers wide, with a total water discharge that dwarfs Angel Falls in volume by an enormous margin. The combined flow of the Iguazu system during peak season reaches around 12,700 cubic meters per second, a figure that lands with a certain physical weight when you consider that 12,700 cubic meters is roughly equal to 5 Olympic swimming pools, and this quantity of water is going over the edge every second. The whole system generates a roar audible several kilometers away and a permanent cloud of spray that creates its own localized weather patterns, including rainbows, typically multiple simultaneous rainbows, that are visible from the viewing platforms throughout most of the day. The Iguazu River, which feeds the falls, drains a large portion of southeastern Brazil before reaching the falls. The cliff over which it drops is the edge of the Parana Plateau, a vast basalt formation produced by one of the largest volcanic eruptions in geological history. the Parana-Itendeka flood basalt event that occurred around 130 million years ago, when enormous quantities of magma welled up through fissures in the Earth's crust and flooded the landscape over an area of roughly 1.5 million square kilometres. The basalt that cooled from that eruption forms the plateau that the Iguazu River has been cutting through ever since, and the falls exist at the point where the river drops off the plateau edge. The falls are not stationary. Like all waterfalls, they are slowly eroding their own cliff face and migrating upstream, retreating from the point where they currently are toward the headwaters. The current position of the falls is roughly 23 kilometres upstream from where they were when they first formed, and the rate of retreat, while slow, is measurable over decades. The Garganta del Diablo, the Devil's Throat, is the central feature of the Iguazu system and the section that generates the most attention from visitors and the most images in travel photography. It is a U-shaped cliff section, roughly 150 metres wide and 700 metres long, on the inside of the horseshoe, where the river pours over the edge in a continuous wall of water, so dense that the bottom of the falls is invisible beneath the spray. The roar at the Garganta is physical, a bass vibration that you feel as much as hear, and the spray soaks anyone who approaches the viewing platform on the Argentine side within a few minutes. On the Brazilian side, the viewpoints allow a more panoramic perspective from across the river, where the full breadth of the system is visible and the scale of it, the 3-kilometre spread of falls, the spray cloud rising to a height of the falls themselves, the constant rainbow arching through the mist, can be taken in as a whole rather than as an overwhelming close-up. The wildlife of the Iguazu National Park, which surrounds both the Argentine and Brazilian sides of the falls, is itself worth noting. Coatis, the long-nosed raccoon relatives of South America, have become thoroughly habituated to tourists in the viewing areas and have developed what can only be described as a professional approach to the snack economy of the park. They move in groups, approach visitors with a confidence that suggests extensive prior experience with the outcomes, and are generally more interested in food than in being photographed, which puts them slightly at odds with most visitors' agendas. They are harmless unless provoked or when food is involved, and provocation and food are, unfortunately, the two things that tourists most reliably provide. The birds of the system include the great dusky swift, Cypseloides senex, which nests behind the falls themselves, on the wet rock faces within the spray zone. These swifts fly through the falling water twice a day, in the morning when they leave to feed, and in the evening when they return to roost, apparently finding this a reasonable commute. They are small and fast and apparently entirely comfortable with having their home address be a cliff face behind a waterfall, which represents a housing choice that prioritizes security over accessibility in ways that most urban dwellers can respect even if they would not personally select it. Niagara Falls occupies a different position in the cultural history of waterfalls than either Angel or Iguazu, not because of its physical superlatives. It is neither the tallest nor the widest nor the most powerful by maximum flow, but because of its proximity to large populations and its role in the history of human engineering, spectacle, and, in several memorable cases, extraordinarily ill-conceived personal decisions. The falls straddle the border between the state of New York and the province of Ontario, 18 kilometres north of Lake Erie, at the point where the Niagara River drops off the Niagara Escarpment, a limestone and dolostone ridge that runs across much of the northeastern United States and southern Ontario. The escarpment was originally the shoreline of an ancient inland sea, and the hard dolostone cap rock that sits on top of softer shale is precisely what produces the waterfall. The dolostone resists erosion while the shale beneath undercuts until the dolostone cap collapses, and the falls retreat upstream by roughly 1 to 2 metres per year as this process continues. The water flow at Niagara is, at its unregulated natural maximum, around 5,600 cubic metres per second, which makes it one of the highest volume waterfalls in North America. However, the flow at Niagara is not its natural maximum most of the time. Since 1950, the United States and Canada have operated under a treaty that diverts a significant portion of the Niagara River's flow through tunnels to hydroelectric generating stations on both sides of the border before the water reaches the falls. During peak tourist hours in the summer season, the treaty ensures a minimum flow over the falls sufficient for visual purposes, approximately 2,800 cubic metres per second, while the remainder goes through the generating stations. At night, and outside the peak tourist season, more water is diverted and the falls run at a reduced volume. This arrangement, which has been in operation for over 70 years, means that the Niagara Falls most tourists see is a regulated visual product, maintained at a level specifically calculated to be impressive, while the actual engineering purpose of the river happens in tunnels underground. This is either a fascinating example of applied hydrology or a deeply cynical piece of scenic management, depending entirely on whether you find out about it before or after your visit. The Niagara Falls has accumulated over roughly 2 centuries of heavy tourism, a remarkable history of human beings deciding to interact with it directly and physically in ways that range from the impressive to the bewildering. The first recorded person to survive going over the falls in a barrel was Annie Edson Taylor, a schoolteacher from Bay City, Michigan, who on October 24, 1901, her 63rd birthday, sealed herself inside a custom-made oak and iron barrel and went over the Horseshoe Falls on the Canadian side. She survived with only minor injuries, emerged somewhat dazed, and reportedly said that she would not recommend the experience to anyone. She made very little money from the stunt and spent her later years in moderate financial difficulty, which suggests that the barrel over Niagara business model had some structural weaknesses that she had not fully anticipated in the planning stage. Approximately 15 people have survived going over Niagara Falls in various vessels and by accident since then, and a roughly similar number have not. The falls continues to be Niagara Falls, entirely indifferent to the human interpretations placed upon it. The erosion of Niagara provides a calibration for the pace at which waterfalls in general modify their own landscapes. At roughly 1 to 2 meters of upstream retreat per year, the falls have moved approximately 11 kilometers from their original position at the escarpment edge since the last glacial retreat created them about 12,000 years ago. At the current rate, and assuming the river's hydrology does not change significantly, the falls would reach Lake Erie in approximately 23,000 years, at which point they would cease to be falls, the river would equalize, and the spectacular geography of the current location would become a set of rapids. This is not an immediate planning concern for anyone currently living in the region, but it does provide a useful illustration of how geological processes and human timescales relate to each other. Things that appear fixed and permanent on any individual human scale are, on geological time, works in active progress. From water falling vertically, the next step is to consider what water carries and deposits when it moves across the surface of landscapes at a slower pace, and this is where the colour question enters the picture. The previous chapters have introduced colour in nature as a side effect of chemistry, the red of Lake Natron from halobacteria, the turquoise of Patagonian glacial water, the orange of the Danakil hot springs. But there are landscapes where colour is not just a feature of the water but of the rock itself, where geological history has been written in pigment across entire mountain slopes, and where the result looks less like a natural landscape and more like a painter's study for something that was never quite finished. The Vinincanca mountain in the Andes of southern Peru, widely known as Rainbow Mountain, sits at an altitude of around 5,200 meters in the Cusco region, which is not a location that encourages casual visitation. The altitude alone produces significant physiological effects on most visitors: headache, shortness of breath, fatigue, the particular light-headed quality of operating on roughly half the oxygen you're used to, and the access involves several kilometers of hiking at that altitude on terrain that is diplomatically not flat. The mountain's appearance, upon arrival and on a clear day, generates a response from most visitors that is out of proportion to the altitude-induced suffering required to see it, which is the highest possible recommendation a natural feature can receive from someone who has just walked 5 kilometers at 5,000 meters. The colours of Vinincanca are not a single hue, but a sequence of distinct bands running across the mountain slope: rust red, cream white, pale green, yellow ochre, deep maroon, pale turquoise, bright orange. Each band corresponds to a different sedimentary layer, and each layer's colour reflects its mineral composition. The red comes from iron oxide, the same compound that colours the Namib dunes and provides rust its characteristic hue. The cream white is calcium carbonate. The pale green is chlorite, a mineral that forms in low-grade metamorphic and sedimentary environments. The yellow ochre is limonite, another iron compound but with a different hydration state than the red variety. The maroon is a deeper iron oxide with clay content. The turquoise is derived from a combination of copper sulfate minerals. The orange involves further iron compounds at higher concentrations. Each colour is a geological signature, a mineral fingerprint that encodes the conditions: temperature, chemistry, pressure, biological activity, under which that particular layer was deposited. What makes Vinninkunka particularly striking is that these layers were not visible until relatively recently. For most of human history in the region, the mountain was covered by a thick glacier and, when not glaciated, by a deep layer of snow and ice. The retreat of the Andean glaciers over the past several decades, a process that has accelerated significantly since the 1980s, progressively exposed the sedimentary layers beneath, revealing the colour sequence that had been hidden under ice for thousands of years. Rainbow Mountain is, in this specific and slightly sobering sense, a product of glacial retreat. The extraordinary landscape is visible because the ice that previously covered it is gone. This does not make the mountain any less spectacular. It does give the spectacle a geological context that is worth knowing. The sedimentary sequence at Vinninkunka dates back to the Mesocenozoic era. With some layers deposited in ancient marine or coastal environments, and subsequently uplifted by the Andean orogenic event, the same tectonic collision of the Nazca and South American plates that built the Andes over the past 75 million years. The compression and uplift that created one of the world's great mountain ranges also folded and tilted the sedimentary layers that had accumulated in the basin before uplift, exposing their edges at various angles across the landscape. Vinninkunka's particular visual drama results from the combination of multiple mineral-rich layers being exposed at a steep angle, creating horizontal colour bands that the human eye reads as an intentional pattern, even though they are simply the sliced cross-section of an ancient sedimentary column. The mountain looks designed because the geological event that exposed it happened to produce a clean, readable colour sequence. It is the geological equivalent of accidentally cutting bread at exactly the right angle to reveal a perfect swirl. The Caño Cristales River in the Colombian department of Meta operates on a completely different colour-producing mechanism from Vinninkunka, and the result is correspondingly different in character. Not bands of pigmented rock, but a flowing river whose bed becomes, for a few weeks per year, a saturated carpet of red, pink, yellow, green, and black that makes it look less like a river and more like an art installation that has gotten slightly out of control. The river is located in the Serranía de la Macarena National Park, a region of the eastern Colombian foothills that is biologically isolated enough from surrounding ecosystems to have developed its own distinct species assemblage. Access to the park requires a flight to the small town of La Macarena, followed by a journey into the park, and for most of the 1990s and 2000s, the region was inaccessible to tourists due to the security situation in rural Colombia, a period during which the river's extraordinary seasonal coloration was essentially unseen by anyone outside the local community and the guerrilla groups that controlled the area. The park reopened to tourism in 2009 following improvements in regional security, and since then the visitor numbers have grown to levels that the park authority now manages carefully with daily entry limits. The colour of Caño Cristales comes from a single plant, Macarenia clavigera, a riverweed belonging to the family Podostemaceae, aquatic flowering plants that attach to rocks in fast-moving water. Macarenia clavigera is endemic to the Serranía de la Macarena, found nowhere else on Earth, and produces a pigment that shifts across a spectrum from pale yellow-green to vivid scarlet, depending on the intensity of sunlight, water temperature, and nutrient levels in the water. At peak conditions, typically from late September to late November, the combination of high light, warm water, and reduced nutrients triggers the plant to produce its maximum pigment concentration, and the riverbed in the stretches where the plant grows most densely turns a vivid, deep red that photographs with an intensity that makes the images look colour-adjusted even when they are not. The yellow sections of the river come from a different species of aquatic plant and from algae. The green sections are moss and other aquatic vegetation. The black sections are the bare riverbed rock, visible where the current is too strong for plants to attach. The white sections are foam and rapid water over smooth stone. The combination of all these elements distributed across a river that runs through waterfalls and pools and rapids over a streambed of ancient sandstone produces a visual experience that is genuinely unprecedented in any other river on Earth. There is nowhere else where a single aquatic plant's pigment response to sunlight has created an entire river's aesthetic identity, which makes Caño Cristales a fairly singular entry in the catalogue of natural wonders, regardless of how crowded that catalogue has become. The name River of Five Colours, while not strictly accurate, the actual colour count varies by season and section of river, and can exceed 5 considerably, is a useful shorthand for the basic character of the place. What the name does not capture is the texture of the experience, which involves the sound of moving water, the feel of the warm, smooth rock underfoot in the shallower sections, and the quality of the Colombian Llanos light in October, which is bright and direct, and renders the reds of the Macarenia with a saturation that most photography equipment struggles to represent accurately. The river is not a landscape you observe from a distance. It is one you walk through, ankle-deep in places with the colour moving around your feet. The thermal terraces of Pamukkale in southwestern Turkey complete this chapter's survey of colour in geological context, and they do so with a material that is simultaneously one of the most familiar and most visually unexpected substances in the natural world: pure white calcium carbonate, which is effectively chalk, travertine and limestone in their various forms. We have already encountered calcium carbonate in the caves of Witomo and the marble chambers of Patagonia, and in both cases water was doing the dissolving. At Pamukkale, the name means cotton castle in Turkish, water is doing the depositing, and the results are as different from caves as it is possible for the same basic chemistry to produce. The hot springs at Pamukkale originate in a geothermally active zone, where the North Anatolian fault system intersects with the broader tectonics of western Turkey, producing hydrothermal water at around 35 degrees Celsius that is highly saturated with calcium carbonate dissolved from the surrounding limestone. As this water emerges from the springs and flows down the hillside, it cools slightly, and the carbon dioxide it carries begins to escape into the atmosphere. As the carbon dioxide leaves, the water's ability to hold dissolved calcium carbonate decreases, and the mineral begins to precipitate out, depositing as travertine on whatever surface the water is flowing across. This is the inverse of the cave-forming process. Instead of water-dissolving rock, it is depositing rock. The same chemistry, run in reverse, produces a completely different landscape. The terraces at Pamukkale have been building for at least 2,000 years, and probably considerably longer, accumulating at a rate of about 2 to 3 millimeters per year on average. The result is a hillside of white terraced pools, some shallow enough to wade in, some deep enough to swim in. Each pool rimmed with a lip of deposited travertine, the whole structure gleaming white against the blue sky of the Denizli province. The terraces extend over an area of roughly 2.5 kilometers, descending the hill in a series of natural steps that have been used as bathing facilities since at least the Hellenistic period. The ancient city of Hierapolis was built at the top of the Travertine Hill, specifically because of the hot springs below, and the ruins of the city, including an extraordinarily well-preserved theatre, a large necropolis and various Roman-era structures, are immediately adjacent to the spring heads. Hierapolis was a significant spa and religious centre in the ancient world, attracting visitors from across the Roman and later Byzantine spheres, which makes Pamukkale one of the longer-running tourist destinations in human history. The springs were apparently providing a reasonable service 2,000 years ago. The business model has held up reasonably well. The white of the travertine at Pamukkale is not a simple flat white, but a subtly varied surface, some sections almost blue-white, some sections cream, some sections with the faint orange-pink of iron oxide contamination in the water. When the pools are full of water, the white travertine takes on a turquoise-blue tone from the water above it, and the contrast between the white rims of the pools and the blue water within them is the visual signature of the site. When the pools are dry, the travertine is purely white and somewhat chalky in texture, the surface dotted with tiny crystalline formations. The management of the travertine terraces at Pamukkale has been a subject of some discussion over the past few decades, because the site was, through most of the 20th century, treated with an aggressiveness that the travertine's relatively fragile nature could not sustain. Hotels were built on the terraces, cars were driven across them, water was diverted for various uses, and the combined impact of these activities had degraded significant sections of the travertine surface by the 1980s. UNESCO inscription in 1988 triggered a series of management changes. The hotels were demolished and removed from the terraced area. Access was restricted to specific boardwalk routes and designated bathing pools, and the spring water was redistributed to flow over sections of the terrace that had been allowed to dry and bleach. The recovery of the terrace surface since these interventions is visible and ongoing, which represents one of the more encouraging outcomes in the history of natural site management. The travertine, given the water it needs and the foot traffic it can tolerate, continues to build itself. The colour theme of this chapter connects across all three landscapes in a way that matters to understand. Vininkunka, Canyo Cristales, and Pamukkale are each coloured by mineral chemistry, and in each case the colour is a direct physical signature of the geological or biological process that created the landscape. The rainbow bands of the Andes encode the mineralogy of ancient sedimentary environments. The red of the Colombian River encodes the biochemical response of a single endemic plant to sunlight and nutrient levels. The white of the Turkish travertine encodes the simple chemistry of calcium carbonate precipitation from cooling thermal water. Colour, in nature, is not cosmetic. It is information, a visible record of invisible processes, a way of reading the planet's history without any equipment beyond working eyes. This is, when you think about it, an extraordinary thing. The Earth writes its geological diary in pigment, and all we have to do is look. The connection between this chapter's theme and the broader series is worth making explicit. We have seen, in the preceding chapters, how geological and biological processes create landscapes of extraordinary visual effect without any intention of doing so. The glowworm cave ceiling that is simultaneously a hunting system and a starfield, the marble caverns whose colour comes from glacial meltwater optics, the volcanic lightning generated as a purely physical consequence of particle collisions, the ancient forest whose moss cover is an ecological community rather than decoration. The colour landscapes of this chapter follow the same principle, but make it more legible. At Vininkunka, the colours are literally a readout of mineral chemistry across geological time, visible to anyone who knows the code and beautiful to anyone who does not. At Canyo Cristales, the colour is a single plant's biochemical response to light and temperature, scaled to a river. At Pamukkale, the white is the visible record of a chemical reaction happening right now, right there, in front of you, at a rate you could measure with a ruler over a decade. None of these places are shows. None of them are performing. They are simply the visible surfaces of processes that would continue regardless of whether any human being ever arrived to observe them. The fact that we find them beautiful is, as this series has argued throughout, our interpretation rather than their intention. But the interpretation is not arbitrary. There is something in the human perceptual and cognitive system that responds to the kind of visual complexity these landscapes produce. The pattern recognition, the colour sensitivity, the sense of scale and proportion, with a response that we call aesthetic experience, and that feels, from the inside, like something the landscape is doing to you, rather than something you're doing to the landscape. The planet has been making remarkable things for 4.5 billion years. It shows no signs of stopping. Colour, as the previous chapter established, is the planet's most legible diary. Cold is something different. It is the planet's most demanding entrance exam. Not every organism can pass it, and the ones that do tend to have arrived at solutions that are, depending on your perspective, either deeply impressive or faintly alarming. Cold strips away options. It closes doors. It reduces the range of viable biochemistry to a narrow corridor, and then narrows that corridor further, and then narrows it again, until only the genuinely committed remain. What is left, in the coldest places on Earth, is not a depleted version of warmer ecosystems. It is something new, life that has been redesigned by temperature over millions of years into forms specifically calibrated for conditions that would kill the organisms of temperate and tropical environments within minutes. Antarctica is where this redesigning reaches its most extreme expression. The continent occupies about 14 million square kilometres, roughly twice the size of Australia, and sits centred on the South Pole, surrounded by the Southern Ocean, which provides the most effective geographical isolation of any landmass on Earth. The nearest significant land is the southern tip of South America, roughly 1,000 kilometres from the Antarctic Peninsula, which is the warmest and most accessible part of the continent. The interior is not warm, it is not accessible. The interior of Antarctica is, by every standard measurement, the coldest place on the surface of the Earth, with a recorded low temperature of minus 89.2 degrees Celsius at the Soviet research station Vostok in 1983. For context, the temperature at which carbon dioxide freezes, dry ice, the substance used in theatrical fog machines, is minus 78.5 degrees Celsius. At Vostok in 1983, the ambient air was cold enough to solidify carbon dioxide. This is not the kind of detail that encourages extended outdoor activity. The continent is also the driest on Earth. Despite being covered in ice, Antarctica is technically a polar desert. The interior receives an average of about 50 millimeters of precipitation equivalent per year, less than the Sahara. The ice sheet that covers it is not the product of heavy annual snowfall, but of the slow accumulation of light snowfall over millions of years, compressed by its own weight into ice that in places reaches over 4 kilometers in thickness. The oldest ice recovered from Antarctic ice cores dates to roughly 800,000 years, and the ice record it contains, bubbles of ancient atmosphere trapped as snow accumulated and compressed, provides scientists with a direct chemical record of Earth's atmospheric composition and temperature across 800,000 years of climate history. The ice sheet is, in this sense, the most detailed climate archive on Earth, a continuous record written in compressed snow that predates modern humans by 790,000 years. Analysing it requires drilling cores several kilometres long from the surface through compressed ice that has not seen the atmosphere since the Pleistocene, which is either extremely tedious or extremely exciting work depending entirely on your feelings about climate history and very cold drills. The wind at Antarctica deserves its own paragraph, because it is not merely unpleasant in the way that wind at most locations is unpleasant. The katabatic winds of the Antarctic interior, gravity-driven flows of cold, dense air that pour down from the elevated polar plateau toward the coast, can sustain speeds of over 240 km per hour for extended periods. These are not gusts. They are sustained winds at speeds that would classify as Category 4 hurricanes by conventional storm categorization systems, except that hurricanes are warm core storm systems, and these winds are simply cold air moving downhill very fast. The combination of -60-degree air and winds at hurricane strength produces wind chill values that are, frankly, not useful to express numerically, because the numbers don't communicate the reality. The reality is that unprotected, exposed skin at such conditions freezes in seconds, and the equipment failures that cold and wind cause are significant enough that Antarctic research programs dedicate substantial engineering resources to preventing them. The South Pole Research Station buildings are elevated on adjustable stilts to allow the drifting snow to pass underneath rather than burying the structures, which speaks to the nature of the ongoing relationship between the infrastructure and the environment it operates in. And yet, the emperor penguin breeds here, not in the milder coastal zones or on the Antarctic peninsula, where conditions approach merely severe. The emperor penguin breeds on the sea ice around Antarctica's coastline during the Antarctic winter, the coldest, darkest, most hostile period of the year, laying its single egg in May or June, when temperatures on the sea ice routinely reach -40 to -50 degrees Celsius, and the polar night means no sunlight for months at a time. The male emperor penguin incubates the egg on its feet, covered by a brood pouch of warm skin, for approximately 65 days while the female is away at sea feeding. During this incubation period, the male does not eat. He stands on the sea ice in Antarctic winter conditions for over 2 months, surviving on fat reserves, incubating an egg. This is, by any reasonable standard of biological assessment, a remarkable commitment to parenthood, and one that most species have sensibly declined to adopt. The colony behaviour of emperor penguins during this incubation period is one of the more elegant collective solutions to a physics problem in the animal kingdom. The problem, in Antarctic winter, standing still on the sea ice in a group is warmer than standing still individually, because a group produces and retains heat collectively. But the individuals on the outside of the group are exposed to the full force of the wind and cold, while the individuals in the centre are warmer. If the outside individuals remain outside indefinitely, they die. The solution: the colony rotates. The penguins on the windward edge of the huddle move slowly toward the shelter of the interior, and the penguins displaced from the interior gradually move around to the windward edge. The whole huddle moves slowly and continuously, like a slow biological conveyor belt, with every individual cycling through both the exposed exterior and the warm interior over time. The result is a thermal distribution system that maintains the colony's collective temperature and prevents the differential mortality that would otherwise destroy it. This behaviour was known from observation for decades before researchers instrumented penguin colonies with temperature loggers and GPS tags to map it precisely. What the detailed tracking confirmed was that the movement is not random. The penguins respond to temperature and wind gradient, with individuals adjusting their movement rate based on their current thermal state. The colony is not following a leader or obeying a central coordination signal. It is self-organizing, each penguin responding to local conditions in a way that produces coordinated global behavior as an emergent property of thousands of individual decisions. The collective intelligence of an emperor penguin colony is, to the extent that the concept applies, distributed across every member of the colony simultaneously, which is either a profound insight into collective behaviour or a good argument for never standing on the outside of a group in bad weather, depending on how you prefer to apply lessons from animal behaviour to daily life. The king penguin deserves distinction from the emperor because they are often conflated in popular media, and they are different animals with different ranges and habits. King penguins are the second largest penguin species, slightly smaller than emperors, and they breed not on Antarctic sea ice, but on the sub-Antarctic islands, South Georgia, the Crozet Islands, Macquarie Island, in conditions that are severe, but not Antarctic interior severe. The king penguin colonies on South Georgia Island are among the largest aggregations of birds in the world, with single colonies containing several 100,000 breeding pairs on beaches that extend for kilometres. A mass of golden-necked birds dense enough that moving through the periphery of a colony requires negotiating a constant stream of penguins that are, individually and as a group, completely indifferent to human visitors in the way that only very large numbers of birds can afford to be. The Patagonian icefields represent the cold chapter's second major landscape. Not the static deep freeze of Antarctic continental ice, but the dynamic systems of glaciers moving, calving, and interacting with the warmer environments around them. The southern Patagonian icefield is the largest temperate ice mass in the southern hemisphere outside Antarctica, covering roughly 12,400 square kilometres across the border regions of Chile and Argentina. The icefield feeds dozens of outlet glaciers that descend from the central plateau toward the forest and lake environments below, and the interaction between those descending glaciers and their surroundings produces several of the more dramatic landscape events available to observers at temperate altitudes. The Perito Moreno Glacier, feeding into Lake Argentino in Argentine Patagonia, is perhaps the most visited glacier in South America and one of the few large glaciers in the world that is currently in a roughly stable state, advancing and retreating in roughly equal measure over multi-year cycles, rather than exhibiting the net retreat that characterizes most of the world's glaciers in the current climate period. The stability of Perito Moreno is a function of the specific geometry of the lake it feeds into and the climate patterns of the region, and it is stable in the long-run average sense rather than in a constant sense. The glacier's front face is in continuous movement, advancing into the lake, periodically blocking the Brazo Rico channel that connects two sections of the lake, allowing water to build up on one side until the pressure causes the ice dam to break. The dam break events, which happen every few years, produce a spectacular and audible collapse of the ice bridge, with sections of ice the size of buildings crashing into the lake in a sequence of cannon-shot sounds that carry across several kilometres of water. The general behaviour of a calving glacier front, even without the dramatic dam break events, is a continuous process of ice breaking from the terminal face and falling into the water below. The sound of a significant calving event carries remarkable distances across the still air of a Patagonian lake environment. A crack followed by a deep, sustained rumbling as the ice falls, then the splash, then the wave rolling across the lake surface, and finally the deep grinding of ice moving against ice and stone. The entire sequence takes place over perhaps 30 seconds for a large calving event, and the resulting iceberg, if substantial, will drift slowly away from the glacier face and gradually melt over hours or days, occasionally rolling as the melt changes its centre of gravity, producing further splashing and further sound. Sitting at the viewing stands at Perito Moreno on a clear day, with the blue-white ice face extending 1 kilometre wide and 60 to 70 metres above the waterline, waiting for the next calving event, is one of the more contemplative outdoor experiences available in South America. The glacier is doing what it has been doing for thousands of years, and you are watching it, and the only thing expected of either party is patience. The ice of a glacier is not a simple solid. It is a polycrystalline material, composed of ice crystals of various sizes and orientations, with grain boundaries between them, compressed under its own weight, deforming slowly under stress. The blue colour of deep glacier ice comes from the selective absorption of red wavelengths by ice at depth. The same photons that pass easily through shallow ice are absorbed progressively as they travel deeper, leaving the blue end of the spectrum to scatter back. The older and denser the ice, the more of this selective absorption occurs, and the deeper and more saturated the blue becomes. Very old, very compressed glacier ice, the kind found deep in the Greenland or Antarctic ice sheets, or in the dense core of a large Patagonian glacier, is a blue so deep it appears almost artificial, a colour that seems too specific and too deliberate to be the product of mere light physics. It is, as you have probably gathered by this point in the series, just physics. The intersection of Antarctic cold and Patagonian glaciation brings us to one of the most dramatic consequences of the cold chapter's long-term trajectory: the shrinkage of ice across the planet. The majority of the world's mountain glaciers are retreating. The Patagonian ice fields are losing mass. The Arctic sea ice extent is declining. The ice sheets of Greenland and West Antarctica are losing mass at rates that contribute measurably to global sea level rise. These are not contested scientific conclusions. They are measured observations confirmed by satellite data, surface measurements, and direct observation across decades. The rate of change in geological terms is extraordinarily fast. The mechanisms are understood, the consequences are in progress. This series is about natural wonders, and the planet's cold systems are among the most extraordinary of those wonders. The ice caves of the Vatnajökull Glacier in Iceland, whose meltwater rivers have carved chambers of vivid blue ice that look like the inside of a jewel. The sea ice of the Arctic, which forms and melts in seasonal cycles that drive global ocean circulation patterns. The ice towers of Antarctica, formed by geothermal heat pushing through the ice sheet in the very few places where the bedrock below generates enough warmth. But honest coverage of the cold chapter requires acknowledging that the cold chapter is changing, and changing faster than any previous human generation has had reason to understand or plan for. The planet has been colder and warmer than the current moment at various points in its history, and life has adapted to those changes on geological timescales. The current rate of change does not offer geological timescales for adaptation. It offers decades. This is a problem of a different kind from any the planet's organisms have previously been required to solve, and whether they solve it as successfully as the emperor penguin solved the problem of incubating an egg in Antarctic winter is, at this point in the story, genuinely open. The cold is not finished with its examination. It continues, at the poles and on the high peaks and in the deep ocean, applying its particular pressure to the organisms unlucky or fortunate enough to inhabit it. And some of those organisms, as we've seen, pass with marks that would impress even the most demanding examiner. From the extremes of temperature, a different kind of natural improbability: geometry. The previous discussion of desert landscapes noted that wind-carved forms can appear almost computationally generated, too complex for random process, too specific for accident. The landscapes in this chapter take that observation further, because they are not complex at all. They are simple, they are precise. They are, in several remarkable cases, mathematically regular in ways that seem to have no business occurring in a natural context. And yet they occur, repeatedly, at different scales and in different materials, as the inevitable product of physical processes operating under specific conditions, with no designer involved and no intention expressed. The Giant's Causeway on the north coast of County Antrim in Northern Ireland is the most visited natural attraction in Ireland and Northern Ireland combined, which is perhaps not surprising given that it consists of approximately 40,000 basalt columns packed together in a formation that looks, at first glance, like someone has tiled a large section of coastline with hexagonal stone pavers. The columns are not identical. They range from 3-sided to 8-sided, with the majority being 6-sided, but the hexagonal columns dominate strongly enough that the overall impression is of a honeycomb floor extending from the cliff base to the sea, the tops of the columns presenting a remarkably flat surface that visitors can walk across. The columns themselves are packed so tightly together that in most sections you cannot insert a credit card between them, which is an oddly specific measurement that nonetheless captures the precision of the fit. There are no mortar joints, there is no adhesive, they simply fit. The formation of the columns involves a physical process called columnar jointing, which occurs when a thick flow of lava cools and contracts. As the basalt solidifies and loses heat, it contracts, and contraction stresses in a solidifying material produce fractures that propagate inward from the cooling surfaces. The geometry of the fractures that minimizes the total energy of the stress field in a contracting solid is, for reasons that are entirely explicable in terms of the physics of stress propagation in materials, hexagonal. The same geometry appears in dried mud, in the basalt of various volcanic provinces worldwide, in the cooling of other materials under the right conditions, and in the hexagonal cells of honeybee combs. The bees arriving at the same geometry through completely different biological optimization processes, because the hexagon is also the shape that divides a flat surface into equal cells using the minimum total perimeter length. Nature, it turns out, has several reasons to like the hexagon, and when the physics of stress propagation and the optimization of material use both point to the same shape, you can reasonably expect to encounter that shape fairly often. The basalt of the Giant's Causeway erupted approximately 60 million years ago, during a period of intense volcanic activity that produced the Thulian Plateau, a vast basalt province covering parts of what are now Northern Ireland, Scotland, the Faroe Islands, Iceland and Greenland, deposited when the North Atlantic was opening and the continental crust was being rifted apart. The magma that produced the causeway flowed across a landscape that was at the time considerably warmer than the current County Antrim coastline, cooled slowly from the top and bottom simultaneously, and produced the column field in a process that took perhaps hundreds to thousands of years. The columns can be up to 12 metres tall in some sections, and the site extends into the sea, with the column formation continuing underwater and reappearing on the island of Staffa off the Scottish coast, where the same geological event produced Fingal's Cave, an almost perfectly arched sea cave in columnar basalt that inspired Felix Mendelssohn to write his Hebrides Overture in 1830, making it one of the few geological features to have directly influenced a significant orchestral composition, which is a fairly distinguished legacy for a cooling lava flow. The local legend associated with the causeway is, as Irish legends tend to be, considerably more entertaining than the geological explanation. The giant Fionn mac Cumhail, in the anglicised version, Finn MacCool, is said to have built the causeway as a bridge to Scotland, so that he could fight a rival Scottish giant named Benandona. The story involves Fionn disguising himself as a baby when the Scottish giant comes to his side of the causeway, his wife presenting the disguised Fionn to Benandona as their infant son. Benandona, reasonably concluding that a baby of that size implies a parent of terrifying proportions, retreats back to Scotland, destroying the causeway behind him. The legend is pleasantly constructed, and has the virtue of explaining both the existence of the causeway and the similar basalt formations at Fingal's Cave in a single narrative framework, which is efficient. The geological explanation involving columnar jointing in a 60 million-year-old basalt flow is less narratively satisfying, but somewhat better supported by the physical evidence. Mount Etna in Sicily produces a different expression of natural geometry, one that operates on a timescale of minutes rather than 60 million years, and requires active volcanic venting rather than cooling lava. Etna is Europe's most active volcano, and it has been erupting with some regularity since before humans began writing things down. The ancient Greeks observed and documented its eruptions, and the volcano appears in Pindar's poetry around 475 BCE as the prison of the monster Typhon. This is either a reference to the volcanic activity or a significant geological coincidence. Etna has been erupting since the 5th century BCE with the consistency of a very reliable geological appliance. Among the features that Etna periodically produces, the volcanic vortex rings are perhaps the most geometrically perfect. When Etna ejects a rapid pulse of gas from a circular vent opening, particularly from the Bocca Nuova crater, the interaction between the gas pulse and the rim of the circular opening causes the gas to spin, producing a toroidal vortex, a ring of rotating gas that rises from the crater and holds its shape while ascending through the air above. The rings can be 20 to 200 meters in diameter and travel at roughly 40 kilometers per hour before gradually diffusing, maintaining their shape for tens of seconds or occasionally minutes before dissolving into the atmosphere. They are, in the simplest visual description, perfect smoke rings, scaled to the output of a large crater rather than a cigarette, and produced by the same basic fluid dynamics that govern smoke rings at any scale. The physics does not change between sizes, the visual effect does. Etna has been producing these rings intermittently for decades, with periods of particularly active ring production coinciding with specific vent geometries and gas pressure conditions. Volcanologists who have studied the rings use them as a non-invasive diagnostic of the pressure and gas composition inside the crater. The ring's diameter, rise speed, and stability carry information about the degassing conditions at depth. What is, to the observer on the ground or watching from the hillside, a remarkably beautiful and almost impossible-looking phenomenon is, to the volcanologist, a gas pressure gauge with unusually good aesthetics. These two interpretations are not in conflict. They are simply operating on different scales of interest. Antelope Canyon in the Navajo Nation near Page, Arizona, does not produce geometric regularity in the sense of the causeway's hexagonal columns or Etna's torus rings. What it produces is something more subtle, the appearance of intentional design in the curves and sweeps of its slot canyon walls, forms so smooth and so composed that they read as the output of a skilled sculptor working in stone. The canyon is a slot canyon, a narrow, deep canyon carved by flash floods through sandstone, and the particular quality of the light that enters through the narrow opening above produces the photographs that have made it among the most reproduced natural interiors in the world, the shafts of light cutting through the red and orange sandstone in compositions that look, consistently, like they have been lit by a professional cinematographer with strong opinions about color grading. The canyon exists in two sections, Upper Antelope Canyon, called Sebikanilini in Navajo, meaning the place where water runs through rocks, and Lower Antelope Canyon, called Hasdistazi, meaning spiral rock arches. The names are functional descriptions of what the canyon does rather than assessments of its appearance, which is either admirable geographic restraint or evidence that the Navajo who lived alongside the canyon for generations had a comfortable relationship with its beauty that did not require rhetorical elaboration. The flood erosion that shaped the canyon operated with a precision that is not, on reflection, imprecise at all. Flash floods in the American Southwest can carry enormous quantities of sand and gravel at high velocity through narrow sandstone passages. As the water moves through the bends of the channel, centrifugal force pushes the sand-laden water against the outer walls, and the abrasive slurry-cut smooth curved surfaces into the soft Navajo sandstone. As subsequent floods cut deeper, the channel narrows at the base where the water concentrates, and the walls above flare slightly. The characteristic slot canyon profile. The smooth, curved, almost polished appearance of the walls comes from the sand acting as an abrasive suspended in water, moving at speed for thousands of years. Each flood event adds another pass of the abrasive, smoothing and reshaping the surface by fractions of a millimeter, building up over centuries to the sculpted forms visible now. The light behavior in Antelope Canyon is what turns a geologically interesting slot canyon into a globally iconic photograph. The narrow opening at the top of the canyon, typically less than a meter wide in the narrowest sections, while the canyon floor below may be reached by staircases descending 10 or more meters, acts as a funnel for sunlight. In the middle hours of the day, particularly in summer when the sun angle is high, shafts of direct sunlight enter the canyon and illuminate the dust particles in the air, creating the visible light beams that appear in most photographs of the site. The sandstone walls themselves, coloured by iron oxide in shades from pale yellow to deep red-orange, reflect and amplify this light, bouncing it back and forth between the canyon walls in a way that produces colours at the canyon floor that do not correspond simply to direct illumination. The floor of Antelope Canyon receives light that has been reflected multiple times from differently coloured sections of the wall, producing colour blending that changes continuously as the sun moves. At peak illumination, the canyon interior glows with overlapping washes of gold and orange and purple that shift minute by minute. Photography in Antelope Canyon is now carefully managed. Tours operate in groups, tour guides position photographers at specific locations at specific times, and the tripod use that was common in earlier years has been restricted to specific tours and times. The canyon receives roughly 100,000 visitors per year, and the management of those visitors through a space that in places is no wider than 2 people standing side by side has required considerable organizational effort from the Navajo Nation, which owns and manages the site. The economics of the site, one of the most heavily photographed locations in the American Southwest, with tour pricing that reflects the demand, have provided substantial revenue to the local Navajo community, making Antelope Canyon an example of natural site management that combines environmental protection with economic benefit to the indigenous owners, which is a less common outcome than it should be. The broader category of slot canyons includes hundreds of examples across the Colorado Plateau, from the well-known to the entirely unvisited, each one a product of the same basic erosion process, operating on the same basic Navajo sandstone, but producing unique results based on the specific geometry of the original fracture, the drainage pattern, and the history of flood events. The Buckskin Gulch near the Utah-Arizona border is the longest slot canyon in the American Southwest at nearly 20 kilometers, and unlike Antelope Canyon, it is accessible only to hikers with technical route-finding skills and a willingness to wade through cold pools of standing water left by previous floods. It offers no light shafts and no organized tours, just continuous slot canyon walls for 20 kilometers, which is a very different experience than Antelope Canyon, but not a lesser one. The geometry chapter's final observation is also its most general. The hexagonal columns of the causeway, the torus rings of Etna, and the smooth sculpted curves of Antelope Canyon are all products of completely different physical processes: thermal contraction, fluid dynamics, and hydraulic abrasion. They look nothing like each other. They operate on different timescales, different materials and different scales, and yet they share a quality. They look like they were made by something that knew what it was doing. This is the defining illusion of natural geometry, and it is not quite an illusion in the way that word usually implies. The processes that produced these forms were, in a physical sense, precise and deterministic. Given the same conditions, the same results would emerge. The hexagons at the causeway are not approximate. The physics of stress propagation in a cooling solid produces hexagons because hexagons are what the physics requires. The slot canyon curves are smooth because smooth curves are what sustained abrasion by water and sand produces. The Etna rings are perfect because the fluid dynamics of a toroidal vortex produces a specific geometry, regardless of scale. The appearance of design is not a trick the landscape is playing on the viewer. It is the landscape accurately reporting that the physics that produced it operates with precision. The precision is real, the designer is not, and the results are, across the entire breadth of the natural world we have travelled through in this series, continuously more extraordinary than the processes that produced them have any obvious obligation to be. This planet, it seems, does not know how to do things carelessly. The previous chapter ended with an observation about precision. The planet does not know how to do things carelessly. It is worth sitting with that for a moment before the final movement of this series, because it contains something that every chapter has been circling around without quite stating directly. We have spent the length of this series travelling through caves lit by living organisms, across salt flats that erase the horizon, over volcanic fields still warm from the last eruption, through forests that have been standing since before recorded history began, across deserts that look like the surface of other planets, into oceans that contain more unknown species than known ones, beside waterfalls powerful enough to atomize their own water before it reaches the ground, up mountains whose colour comes from the mineral chemistry of an ancient seabed, through the coldest places on Earth where life continues anyway, and along coastlines tiled with mathematically precise basalt columns that no one designed. And in every case, the explanation has been the same: physics, chemistry, time. No intention, no plan. Just the universe operating according to its own rules, with no awareness of and no interest in what the results look like. And the results are extraordinary. This is the puzzle. Not a puzzle in the sense of something that cannot be resolved, but a puzzle in the sense of something that continues to be worth noticing. Because the gap between the ordinariness of the cause and the extraordinariness of the effect is, across the full catalogue of this series, remarkably consistent. Consider, briefly, the scale of what this series has actually covered. The geological time represented in these landscapes spans from formations deposited over 400 million years ago in shallow tropical seas, the limestone of Waitomo, to lava flows added to the Big Island of Hawaii last week. The biological time spans from the Laurisilva's Miocene ancestry 30 million years ago to the glowworm larvae that will complete their metamorphosis and die within a few weeks of the moment this is being read. The physical distances span from the lightless floor of the Challenger Deep, 11 kilometers below sea level, to the summit of Vininkunka at 5,200 meters above it. A vertical range of over 16 kilometers of Earth's surface, all of it occupied, all of it shaped by the same basic forces operating in different combinations at different intensities. Every landscape in this series is, in its own way, a demonstration of range, of how far the same basic chemistry and physics can extend when given different starting materials and sufficient time. Water dissolves limestone and produces the Waitomo caves. Unremarkable chemistry, applied patiently over millions of years, produces a cathedral ceiling that glows blue-green with living light. Glacial meltwater erodes marble and produces chambers whose walls reflect turquoise. Salt precipitation from an ancient lake produces a 10,000 square kilometre mirror that erases the boundary between earth and sky. Lava cooling in a specific geological context produces 40,000 hexagonal columns, so precise that you cannot insert a credit card between them. Flash floods cutting through sandstone produce smooth curves that look like the work of a sculptor who had been practicing for a very long time. Not one of these outcomes was aimed at. Not one of them was the purpose of the process. They are, each of them, the side effect of something the Earth was doing for reasons entirely unrelated to visual impact. This matters, and here is why. It means the catalogue is not finite. It means that the processes which produced everything in this series are ongoing, and they are producing new results. And those results include things we have not found yet, things we do not know to look for, things that will be discovered by someone with a scientific instrument, or a diving apparatus, or a satellite sensor, or simply a pair of walking boots in a region of the planet that receives insufficient tourist attention. The planet is not a museum of completed works. It is an active workshop, and most of its floor space is still unexamined. The Pamukkale terraces are growing. Each day, the thermal springs of the Denizli region deposit another fraction of a millimetre of calcium carbonate on the travertine surfaces, extending the pools, building the lips, adding incrementally to a structure that has been building for at least 2,000 years and possibly considerably longer. The rate is slow by human standards. The terraces do not noticeably change between one visit and the next, or between 1 year and the next, or in some cases between 1 decade and the next. But the accumulation is continuous, and the chemical process is as active today as it was when the ancient city of Hierapolis was first established above the springs in the Hellenistic period. Visitors today are walking on a surface that is still being built around them, which is either a slightly vertiginous thought or a pleasantly dynamic one, depending on your relationship with geological time. Kilauea is building. The lava that pours from its vents and flows into the Pacific Ocean is adding to the big island of Hawaii in real time, extending the coastline, building new land from the ocean floor upward. As noted in the volcano chapter, the island of Hawaii is currently sitting directly above the hotspot that has been building the Hawaiian chain for tens of millions of years. And the process that built Oahu and Maui and Kauai is the same process currently working on the Big Island. The island you can visit today is larger than the island that was there last year. Not by much. The rate of addition is measurable, but not dramatic on a human scale. But the addition is happening, which means that in any meaningful sense the island is still being created. The lava flowing into the ocean off the Puna coast is not an event. It is a continuation. Niagara is moving. The recession of the falls upstream, that 1 to 2 meters per year that geologists can measure by comparing historical surveys, has been continuous since the falls formed roughly 12,000 years ago. The position of the falls today is not the position they were in last century or last millennium. The Antelope Canyon slot is deepening. Each flash flood that moves through the narrow Navajo sandstone channel carries an abrasive load of sand and gravel that removes another fraction of a millimetre from the smooth walls, cuts a little more depth into the channel, refines a little more of the curved geometry that makes the canyon's light behaviour so extraordinary. The canyon that exists today is not identical to the canyon that existed before last year's flash floods, or the year before that. It is incrementally different, and the differences accumulate over decades and centuries into measurable changes in the canyon's profile. The smooth, sculpted quality of the walls is not a static condition. It is a process that has been running for thousands of years and continues to run with every flood event. The canyon is being remade continuously by the water that carved it. The Amazon is cycling. The moisture that transpires from the trees of the Amazon basin rises, condenses, falls as rain, is absorbed by roots, transpires again in a water cycle that operates largely independently of the ocean evaporation that drives rainfall elsewhere in the world. Every day, the forest produces and recycles the water that sustains it, in a closed loop that has been running for millions of years. The individual trees in this loop are finite. They grow and die on timescales of decades to centuries, but the loop itself continues, maintained by the collective function of billions of trees operating in parallel, replacing themselves through seed dispersal and succession as individual trees fall. The forest is not the trees. The forest is the process, and the process has been running since before the Andes were fully formed. The laurisilva of Madeira is accumulating moss. Every decade, the moss communities on the ancient laurel trunks add another layer of growth, deepening the upholstered texture that makes the forest look perpetually damp and perpetually old. The oldest sections of the laurisilva contain moss communities that have been developing for centuries on individual trees, communities of dozens of species layered over each other in a depth of ecological complexity that takes decades to re-establish once disturbed. The forest is not just standing. It is being maintained continuously by the fog drip from Atlantic trade winds, by the root systems of trees that have been in place for generations, by the accumulation of dead organic matter that builds the forest floor's nutrient structure year by year. The Giant's Causeway is eroding. The wave action that beats against the basalt columns on the Antrim coastline removes material very slowly from the exposed faces of the columns. Joints widen, blocks loosen. Sections of the formation that extend into the sea are subject to chemical weathering from the constant saltwater contact, and the material lost to the sea is not replaced. The causeway, unlike Pamukal or the lava fields of Kilauea, is losing material rather than gaining it. It is a landscape in net decline, slowly being consumed by the sea that surrounds it. On the timescale of human observation, it appears static and permanent. On geological time, it is being worn down, and in tens of millions of years it will not exist in its current form. This is the correct fate of basalt columns on a coastline, and there is nothing particularly alarming about it. But it serves as a reminder that the planet's construction projects and its demolition projects are simultaneous and ongoing, and that the things we consider permanent are consistently works in progress. The Antarctic ice sheet is flowing. Ice at the base of the polar ice sheet, under the pressure of kilometers of overlying ice, deforms and moves slowly toward the coast, carrying the upper layers with it. The ice sheet is not static. It is a slow, cold river, moving at rates of centimeters to meters per day, depending on the location and the underlying bedrock conditions. Where the glaciers reach the coast, they carve icebergs into the Southern Ocean, carrying the ice and the ancient atmospheric record it contains, into the sea where it melts and mixes with the ocean water. New snow falls on the polar plateau, compresses, becomes ice, and begins the slow journey toward the coast. The ice sheet is a conveyor, moving material from the interior to the perimeter in a cycle that has been operating for millions of years, and the bubbles of ancient atmosphere that the ice cores reveal were once at the surface before being buried and transported and eventually returned to the atmosphere on the other end of the conveyor at the calving front. The ice sheet breathes, in geological time, on a very long exhale. The hydrothermal vents on the deep ocean floor are venting. At this moment, in the complete darkness of the deep Pacific and Atlantic and Indian Oceans, the hot, mineral-rich water is pouring from vent structures on the seafloor. The chemosynthetic bacteria are processing the chemical energy in the vent fluid. The tube worms are feeding on the bacteria. The crabs and shrimp and fish of the vent community are moving through the warm water around the vent structures. This is happening right now, has been happening continuously since the first hydrothermal vent systems formed in the early ocean, and will continue to happen for as long as the Earth's interior retains sufficient heat to drive hydrothermal circulation through the oceanic crust. The deep-sea vent communities discovered in 1977 were not new. They were simply newly visible to us. They had been operating in the same way, in the same darkness, for the entire length of geological time since the ocean floor was first permeated by hydrothermal water. The Salar de Uyuni is reflecting. During the rainy season on the Bolivian Altiplano, right now, a thin layer of water sits on the salt flat, and the sky above it is doubled, the clouds appearing both above and below as the 10,000 square kilometre mirror does what it does. The geometry of that reflection, the light travelling from the sky to the water surface and back to the observer's eye, is a simple optical phenomenon, the same physics that produces any reflection in any still surface of water. The surface just happens to be very flat, very large and very clear, because it has been deposited and smoothed over thousands of years of salt precipitation from an evaporating lake. The mirror is not a special event, it is what happens when those specific conditions are met, and it happens every rainy season, and it will continue to happen for as long as the Bolivian Altiplano receives seasonal rainfall and the Salar de Uyuni retains its extraordinary flatness. The cave glowworms are glowing. In the Waitomo caves, in the dark, the larvae of Arachnocampa luminosa are hanging from their silk threads, with their bioluminescent organs active, their sticky threads waiting for insects to fly into them. The cave ceiling producing its blue-green star field for no audience other than the organisms that happen to share the space. This has been happening continuously for as long as the cave system has been old enough and dark enough to support the glowworm colony, which is a very long time by any standard. The tourists who float through in their silent boats on guided tours are visitors to a process that was running before tourism existed and will continue running after it has been replaced by whatever comes next. The Caño Cristales is changing colour. Right now, if it is between September and November, and the conditions of sunlight and water temperature and nutrient level in the water are right, the Macarenia clavigera in the Colombian River is producing its pigment at maximum intensity, and the riverbed in the sections where the plant grows most densely is red, a colour so saturated it looks wrong for a river, a colour that exists because one specific plant species on one specific river in one specific range of conditions has evolved one specific biochemical response to those conditions. The colour exists for no observer. It would be precisely as red if no human being had ever found the river, if the Serranía de la Macarena had remained inaccessible indefinitely, if the security situation in rural Colombia had never improved. The plant is not performing. It is simply expressing its biochemistry, as it does every year, in the river that it has inhabited for much longer than any human community has been nearby to notice. This is perhaps the most honest way to understand everything in this series. Not as a collection of the planet's greatest visual achievements, curated for human appreciation, but as a selection of ongoing processes that happen to produce, as a consequence of their operation, things that human beings with visual systems and pattern recognition capabilities and a capacity for aesthetic response find extraordinary. The Waitomo glowworms would light the cave regardless. The marble caves of Patagonia would be turquoise regardless. Kilauea would pour lava into the sea regardless. The Antelope Canyon curves would deepen with each flood regardless. None of this depends on our presence, and yet our presence changes something. Not in the geological or biological processes themselves, which are indifferent to observation, but in the observer, the person who stands at the edge of the Perito Moreno glacier and hears the cannon-shot crack of a carving event and watches a building-sized block of ice fall into the lake is not the same person they were before that moment, in some small but real sense. The experience of scale, of genuine, physical, felt scale, recalibrates something. The diver who descends through the jellyfish of Elmalk Lake and moves through millions of golden, soft-bodied animals that cannot sting them, in warm, clear water, in complete silence, carries that experience in memory as a reference point for what the natural world is capable of producing. The walker in the Lorisilva, who puts their hand on a moss-covered trunk that has been in the same spot for 300 years and feels the deep, damp cool of a forest that has never been anything other than a forest, is touching a continuity that extends backward through time, far beyond anything human culture has managed to produce. These experiences matter, not because the planet needs us to have them. It does not, but because we do. The sense of being embedded in a world that is vastly larger, older, more complex and more creative than human activity can produce or comprehend is not a comfortable sense exactly. It has in it an element of smallness that some people find troubling, but smallness in the right context is not a diminishment, it is a correction. The correction that comes from standing next to Iguazu Falls and understanding that the sound you are hearing is 12,700 cubic meters of water per second, that the mist you feel on your face has been travelling through the drainage of southeastern Brazil for days to arrive at this escarpment edge, that the escarpment itself was created by one of the largest volcanic events in planetary history 130 million years ago. That correction is useful. It puts the human scale in its proper relationship with the planetary scale, which is the relationship of a brief and recent resident to a house that was built long before they arrived and will stand long after they are gone. The house, to extend the metaphor perhaps one notch beyond its structural capacity, is not finished. It has never been finished. It is being renovated continuously by forces that do not consult blueprints, do not take breaks, and do not care whether the results match any prior expectation. It is also worth noting, with some directness, that the renovation team has been working on this project for considerably longer than any human project has ever been attempted. The Great Pyramid of Giza has stood for approximately 4,500 years, which is impressive by any human measure. The basalt columns of the Giant's Causeway have been standing for 60 million years. The laurel trees of the Madeira Laurisilva have continuous ancestral lineages stretching back 30 million years. The hydrothermal vent communities of the deep Pacific have been operating since before the Himalayas existed in their current form. When we talk about ancient human monuments and the extraordinary achievement of building things that last centuries or millennia, We're talking about timescales that the planet uses as rounding errors. This is not a criticism of human achievement. It is simply a calibration exercise, and it is useful to perform occasionally. The renovation includes both construction and demolition, sometimes simultaneously in the same location. The coral reefs being built by Acropora and Poritz polyps in the shallow, warm Pacific are also being bleached by water that is too warm for their zooxanthellae to tolerate. The travertine terraces of Pamukkale are still growing on the hillsides they have been building for 2,000 years. The slot canyons of the Colorado Plateau are still being carved by floods that will eventually remove enough material that the canyons collapse into open gulches and the slot geometry is lost. The glaciers are retreating from positions they held for thousands of years. The volcanoes are building new land from the seafloor. The wind is still carving the chalk of the Egyptian desert into mushroom shapes that will eventually be worn down to stumps and then to nothing. All of this at once, all of it continuous, all of it operating on timescales that make the entirety of human history look like a Tuesday afternoon in the geological record. The planet does not need to be appreciated. But it rewards appreciation with the particular satisfaction of understanding, not full understanding, which is not available and probably not achievable, but the kind of partial, provisional, endlessly extendable understanding that comes from paying close attention to things that repay close attention. The glowworm cave rewards close attention with the knowledge that each point of light is a lava in a silk hammock waiting for dinner. The basalt columns reward close attention with the physics of contraction stress. The sleeping sperm whale rewards close attention with the fact of a 50-ton animal dozing at the surface of the Atlantic on the buoyancy of its own spermaceti. The rainbow bands of Vininkunka reward close attention with the mineral biography of an ancient seabed, lifted by tectonic collision and exposed by glacial retreat, reading out its history in iron oxides and copper sulfates on a slope in the Peruvian Andes. None of this is decoration. All of it is information. The planet has been writing it for 4.5 billion years, in materials ranging from calcite to basalt to salt to living tissue, in formats ranging from cave ceilings to river chemistry to ice cores to columnar basalt formations on the coast of County Antrim. The writing is ongoing, the archive is incomplete, and the part of it that has been examined so far, the small, remarkable, continuously surprising part that this series has tried to cover, suggests that what remains to be found is considerably more extraordinary than what has already been catalogued. There is a useful exercise here, which is to think about what this series did not cover. It did not cover the stromatolites of Shark Bay in Western Australia, living mats of cyanobacteria that build layered carbonate structures in shallow saline water, representing a type of organism whose fossil record extends back 3.5 billion years, making them among the oldest forms of life with a continuous lineage visible in the geological record. They look, to the casual observer, like rounded stones scattered on a tidal flat, which is perhaps why they do not feature more prominently in nature documentaries. They are, however, among the most significant living organisms on Earth from a historical perspective, and the fact that they are still here, still building their slow carbonate mounds in a corner of Western Australia, says something about persistence that the more visually dramatic entries in this series cannot quite match. It did not cover the Richat structure in Mauritania, a roughly 50-kilometre wide circular feature in the Saharan rock that was for decades assumed by pilots and early satellite analysts to be a large meteor impact crater, and which turned out, on closer geological examination, to be a deeply eroded geological dome, the result of an ancient volcanic intrusion being differentially eroded over hundreds of millions of years to produce a series of concentric rings of different rock types, each ring a different colour, the whole structure visible from orbit as a bullseye pattern on the desert surface. The Richat structure is sometimes called the Eye of Africa, which is an appropriate name for something that looks exactly like an eye and is located in Africa. It did not cover the morning glory clouds of the Gulf of Carpentaria in northern Australia, a rare meteorological phenomenon in which extremely long roll clouds, sometimes stretching over 1,000 kilometres, form near the coast at dawn and move inland, a single cloud formation longer than most countries. The mechanism involves sea breezes, terrain effects, and the specific atmospheric conditions of the Gulf region, and the result is a cloud formation so consistent in its occurrence and so dramatic in its scale that local Aboriginal communities have incorporated it into their cultural knowledge for thousands of years, while the broader meteorological community spent much of the 20th century debating what caused it. It did not cover the Socotra archipelago in the Arabian Sea, a group of Yemeni islands so isolated by the Indian Ocean monsoon patterns for so long that they have developed a flora unlike anything else on Earth, including the dragon blood tree, Dracaena cinnabari, which grows in an umbrella shape with a trunk like stacked discs and a canopy so dense it can be used as shelter from rain, and produces a bright red resin from its bark that has been traded since ancient times for use in dyes, medicine, and incense. The dragon blood tree looks, in photographs, like an illustration from a book that was illustrated by someone who had never actually seen a tree and was working from a description. In person, presumably, it continues to look like that. The catalogue of what this series did not cover is itself a natural wonder, and it stretches in every direction across the planet's surface and into its depths. This is not a failure of the series. It is, rather, the correct state of affairs for a planet of this size and this age and this variety, addressed by a project of finite length. The series has covered what it has covered, and the planet has reserved, with complete indifference, an essentially unlimited amount of additional material for future consideration. The writing is ongoing. The archive is incomplete. This has been, from the first cave to the last glacier, a series about one thing: a planet that does not know how to stop being interesting. We have travelled from underground caves glowing with bioluminescent larvae to salt flats erasing the horizon, from volcanoes building islands in real time to forests that predate human civilization by millions of years. From desert badlands that look like alien worlds to deep ocean trenches where plastic bags have beaten us to the bottom. From waterfalls 979 meters tall to rivers that run red with a single plant's biochemical response to sunlight. From the coldest continent on Earth where penguins solve thermodynamics problems as a colony, to basalt coastlines where the lava cooled into hexagons, because hexagons are what the physics required. In every case, the mechanism was simple. In every case, the result was not. That gap, between the simplicity of what the planet was doing and the complexity of what it produced, is the thing this series has been pointing at all along. It is not a gap that closes on closer inspection. It widens, because every layer of understanding reveals further layers below it, and the further down you go, the more clearly you see that what we call natural wonders are not exceptions to the rule of an otherwise ordinary planet. They are the rule. They are what happens when matter and energy and time are left to operate according to physics, without intervention, without design, without any ambition other than the continuation of the processes that govern them. The planet is not trying to impress anyone. It has never been trying to impress anyone. The fact that it impresses us, consistently and profoundly, across every continent and every ocean, and every altitude and every geological period, is entirely our problem, and what a problem to have. One last observation before the series concludes, which is this: the planet's most extraordinary features are not, in any meaningful sense, finished. They are mid-process. The glowworm cave is mid-colony. The marble chambers are mid-erosion. The salt flat is mid-evaporation. The volcano is mid-eruption in the geological sense. The forest is mid-succession. The reef is mid-construction and mid-bleaching simultaneously. The glacier is mid-flow. The canyon is mid-carving. The basalt columns are mid-erosion. Every single landscape in this series is a frozen frame from a longer film, and the film was running before humans arrived to watch it, and will continue running after we have gone. What this means for anyone watching this, anyone who has made it this far through caves and deserts and oceans and ice and coloured mountains and geometric coastlines, is that the natural world is not a collection of things to see before they disappear or change. It is a collection of ongoing stories, each at a different point in its narrative, each operating on a timescale that dwarfs any individual human life, but is not, in principle, inaccessible to human understanding. The travertine terrace you could visit at Pamukkale today will be slightly larger next year. The lava coast at Kilauea will be slightly longer. The Niagara Gorge will be slightly longer. The Antelope Canyon walls will be slightly smoother. The Laura Silva mosses will be fractionally thicker. These are not significant changes in any individual year. But they are real changes, and they are in the same direction they have been moving for thousands of years, and they will continue in that direction long after anyone reading this has concluded their own, considerably shorter, geological footnote. The planet builds, it always has, it always will. And we, for the brief and improbable duration of our presence on its surface, have the extraordinary privilege of watching it work. Sweet dreams, everyone. The planet will still be here, and it will still be building when you wake up.